So our next speaker is Gilles Loup from the University of Liège, and he's going to be talking about highlights of machine learning.
Okay, so for those of you who have never been to PHYSTAT, if it's the first time you are on this workshop, at the end of the workshop, we are used to have highlights. So these are like summary talks from different perspectives. So given that my background is machine learning and SBI, I will mostly focus on that aspect, and then you will have other perspective by other speakers. Okay, so I've structured my summary talk as a list of basically takeaways, main messages that you could apply or that maybe you should remember. And the topic I will mainly focus on is the one of simulation-based inference for obvious reasons. The first one is that it seems that finally simulation-based inference seems to be taking off. So we had a few months ago in Munich a whole PHYSTAT workshop dedicated to the topic. And during this meeting, we've had also many talks, either fully covering SBI or applications of SBI, or at least mentioning in one way or the other the topic. So I will not re-describe exactly what is SBI, what this is about. Even though there is one aspect which I think is quite important. So usually when you describe SBI, you say that you have a simulator which corresponds to your theoretical model. This simulator is stochastic, it takes as input parameters, and then it generates data. And then what you want to do, given this model, is to do inference. So you want to reverse the process, given some data that you collect in your experiment, you want to retrieve parameters that are compatible with this data. And so you can do this from a Bayesian perspective. In this case, you would obtain, or you would like to estimate a posterior distribution over the parameters, or in a frequentist way. Okay, and usually when you tell the story, we start by saying that this is challenging for the reason that the likelihood is intractable. If the simulator is stochastic in some very intricate ways deep inside the simulators, then that means to be able to evaluate the likelihood function, so the density associated to a parameter theta given and a data point x, you need to solve this huge integral over all the latent variables z. And that's the reason it's intractable. My first take-home message is that actually you can apply SBI even when the likelihood is tractable. And there is a point in doing that. We had a talk on the topic of gravitational wave inference by Maximilian Dax on the topic. And this is a case where actually the likelihood is tractable. So the simulation is described as a forward deterministic process relating parameters to data, and then it's only at the very end that you add a bit of noise, usually additive noise like Gaussian noise. And in this case, you can actually evaluate the likelihood exactly. So why do we care then about SBI in this setting? The reason is that one of the main reasons is amortization. So if you can amortize the process of doing inference, then retrieving a posterior is as fast as doing one forward pass to your inference network, which is much faster than repeating, for example, a whole MCMC analysis, which could take hours or days. Okay. So first takeaway, SBI can also be used and has value even when the likelihood is tractable. So actually in this meeting, we've had only one example, unless I've missed another of this case. So I will just mention another. This is a previous work that we did with a PhD student of mine. She's studying exoplanets, and she's exactly in the same setting. She has a simulator of atmospheres of exoplanets, which is described as a deterministic process from parameters to spectrum, and it's only at the very end that you add a bit of noise. And so really the final simulator output is given by just some deterministic function which is really implementing the physical process plus some noise, okay? And again, in this setting, we found that it's much, that there is a value in doing SBI. First, because of amortization, it's much faster if then you want, for example, to analyze catalogs in which you may have hundreds or thousands of analyses to repeat. And second, another important point in my opinion is that because of amortization, you can also try to diagnose the quality of your inference results. It's much more complicated to assess that the posterior you would obtain, let's say with MCMC, is close from being correct. There are, of course, ways to do that, but it's tricky. Second takeaway, another unexpected maybe application of SBI is unfolding. So as far as I understand, I can view unfolding as simply an aggregated posterior. So you start from data, in this slide, X Rico, and then you want to go from data to particle level, so X part, and this is an inverse problem. You want to go from data to something that happened before, and so this component is actually the result, or can be viewed as the result as an inference. And so you just have to repeat this inference over and over the data points that you have that you've collected, and then you aggregate everything, and at the end you recover a prior, which happens just to be an aggregation of posteriors. Okay, third takeaway is that even though SBI was mentioned quite many times, is that when it comes to actually use it and claim scientific results with these techniques, these studies then, they come with very strong requirements in terms of accuracy and reliability. So Max mentioned his story, explained everything that he needed to do in order to convince the LIGO collaboration to use SBI for inference. And from what he told me, it's actually they don't use it yet fully, it's still mostly based with MCMC. So there is still a bit of convincing to do. But really what you have to show what he had to show then was basically this technique. It comes with neural networks and whatnot. You really have to work very hard to show that, okay, it's at least better than the current method, and also it comes with benefits. We had more or less the same story with Eshik, where he mentioned that the challenges of neural simulation-based inference involve robustness, uncertainties, and other things like the Neumann construction. These are things that you need to do really if you want to use SBI to produce scientific results. Okay, so if you have these requirements, you need ways to basically assess the quality of your results. So the first thing that you should remember is that SBI does not give you the correct answer. It's always an approximation, for example, of some posterior. Okay, so you need a way to assess if this approximation is far or not from the actual posterior that you want to estimate in the first place if you are Bayesian. So there are various diagnostics that you can use for this purpose. So a few talks cover this topic. So Kyle mentioned and others mentioned classifier-based diagnostic that you can use basically as a pre-weighting mechanism. And then you can check if, for example, the likelihood ratio you would obtain with an NRE is a good reweighting. That's something you can do. There are other techniques like calibration curves that you can look. You can also look at coverage curves. These are the tiny ones that we worked on a lot with my team. So there are various ways that you can, various techniques that you can use to assess the quality of your approximation. There is a fine print that you should remember is that most of these diagnostics, almost none of them, I think there is only one of them, so none of them provide sufficient guarantees. It's not because you pass the diagnostic that your posterior is correct. Okay? However, if you fail the diagnostic, then you can be sure that you are wrong. So what do you do then to convince yourself that your results are at least close enough to be correct? Well, you can look at many plots. This is usually what we do. So Eshik had this slide where he populated with so many plots to look at. For example, when you train a generative model, you have to do all these checks about whether or not it reconstructs some physical properties of the process that you're trying to simulate. So all these things are things you should look at. if you want to convince yourself that you are doing a good job. Unfortunately, and that was one of the take-home message of Eshik, is that there is no automated way to do that yet. Okay. Okay, so let's say you do one of these two things. You use diagnostics, or you look at these plots, like posterior predictive checks and whatnot, and you find that something is wrong. So what if the diagnostics that I'm telling you to use tell you that you are wrong? What should you do? So the one, and this is now me talking as a machine learner, one thing that you should all remember is that the heavy lifting is done by a neural network. And this neural network, of course, will be the reason, or certainly will be the reason that your inference results are wrong. So how do you improve a neural network? This then leads me to my fifth take-home message. The 2024 recipe to make neural networks better is to have more data, to have more parameters, and to train for longer, to have more compute. Okay? And again, I'm taking Mac's example here. This is not something he really spent time on, but if you go and look actually at the supplementary materials of his papers, this is something which is said. So for example, you need more data. And one nice trick about deterministic forward model plus noise is that you can build very easily some kind of infinite data set. You just simulate forward many, many times, like a million of times, up to the end of the deterministic pipeline. You freeze this, you save that on disk, and it's only when you train, when you build your mini batches, that you add the bit of noise. And for each mini batch that you produce, you resample this noise. So that leads to some kind of infinite training set. And this is the trick that he used. We construct training set based on 5 times 10 to the 6 set of intrinsic parameters, so theta values, but by sampling extrinsic parameters and noise realization during training, so when building the mini batches, the effective size of a training set is infinite in these dimensions. So this is one trick that you should use if you are in this setting of deterministic process plus a bit of noise. Second, more parameters. So this is something that, again, we don't realize, but if you really want to make this inference network very precise, you need to spend a lot on the architecture of this, a lot of time on the architecture of this neural network. And in this case, again, in the supplementary material, you find that the flow, the normalizing flow, consists of 300 hidden layers. So that's a very deep neural network. In total, the embedding network and the flow combined have roughly 10 to the 8 learnable parameters. So that's a lot. And finally, more compute. So you need to train this beast, and you need a lot of compute power to do that. So in this case, it says that training for 450 epochs with a batch size of 4,000 takes roughly 10 days on a single GPU. Okay, and this is for the very best neural network that you find at the very end of your parameter tuning. Okay, of course, I'm sure he repeated that process tens, if not hundreds of times. Okay, what if this is not enough? So there are ways to improve the inference network further. One way is to, and this is what I call regularizations, it's to regularize basically the inference network. And we have seen a couple of ways, so a couple of ways at least have been mentioned in that direction. One of them was mentioned by Eshik, in which he said very briefly that in his SBI analysis, he's not using one neural network, but he's using actually an ensemble of neural networks. So this is a very well-known story. If you did machine learning back in the days in 2015, of course, you should use ensemble of models. That's the default recipe. If you were playing Kegel, for example, and trying to win competitions, you need to ensemble different models. So what does that mean? If you don't know, the idea is very simple. You have your training set, you train once, you obtain, for example, the first neural network, but then you repeat. You train a second neural network, you train a third, you train a fourth, you train a fifth, you train thousands of them if you can. And the reason you do that is that because the training procedure is randomized, you train on random mini batches, so you will not exactly obtain every time the same solution. When you aggregate the predictions of all these neural networks together, for example, by taking the mean prediction as the final prediction, then it will basically smooth out the predictions. And so this is well studied. It's basically reducing the variance of the model, and it comes with good properties. If you were to do something very similar, which is to use a BNN, a Bayesian neural network, then at the end, the Bayesian model average would also come with this nice property of smoothing out the prediction. Except, and this is just a slight comment, technical comment, a BNN and an ensemble are not exactly the same, and a BNN does not average over the randomness of our training procedure, just average over the random weights and the beliefs that you associate to these weights. But if you were to repeat, or if you were to build basically an ensemble first and a BNN second, you would not obtain the same results, which means that the BNN does not capture the randomness of the training procedure. Okay, so you can do that. Another way to do that, to regularize the neural network, is something we worked on for a couple of years with a few PhD students of mine, mostly Arnaud. And it's basically a way to, by construction or during training, you know that your neural network will not be correct. But at least what you can do is to force it to be conservative by design. Okay, so you can force basically the posterior to be larger than what they should be, in which case you know that the inference result, okay, they will lose in terms of statistical power, but at least you would not make wrong inferences. And so there are several ways to try to enforce this conservative behavior. You can have a look at these two papers in which we make both the NRE algorithm and the NPI algorithm conservative. And basically what happens is that if you compare, for example, NRE against this conservative version, if you compare the coverage curves, you see that after this trick, after regularization, all the coverage curves appear above the diagonal, meaning that they are in the conservative regime. And this is the case also for NPE against BNP. Okay, what if you do all of this, but this is not enough? My next take-home message is to say then that you should try to put domain knowledge directly into the inference network. It's one thing to make it deeper, that will help. It's one other thing to train it on more data, that will help. But maybe it's not enough. Maybe you will be hit by the curse of dimensionality and there is nothing you can do about that. So you need to basically hard code assumptions, physical domain knowledge, directly into the architecture of the neural network. And so we have seen two examples along this direction. One of them was the alligator architecture, in which basically you by construction have a transformer which is equivariant to some transformation. And so you need to think very deeply about how to put this domain knowledge inside neural network layers, but that's something you can do. And if you manage to do it, then of course you see that the benefits are huge in terms. So this is a curve which shows the classifier AUC of regenerated data. And so what you want is for this curve to be as low as possible and close to 0.5 if you can. And so when you compare an MLP, a regular neural network without any assumption, or a regular transformer without any assumption about the process, and you compare that to the alligator transformer, then what you see is that for the same size of the training set, you reach a lower, in this case, neural classifier AUC, when you have these assumptions directly built in the architecture. And of course, there is a reason beyond that, is that if indeed these assumptions are correct, then an MLP or transformer which is not hard-coded with these assumptions will have to rediscover this from the data, and that will consume your training budget. Another example, again, is from Max, in which he equipped the inference network with group equivalence properties on the time shift of the input signal. And again, that helps actually a lot to produce even more accurate results. Okay. Next takeaway, and I think this is a very nice takeaway. If you can evaluate the likelihood, if the likelihood is tractable, please use it. And we have seen that if you can use it to do importance sampling, and you should see that really as some kind of cheat code to obtain exact inference. If you have an approximate inference network, but you can evaluate the likelihood, then you can basically correct the imperfection of the inference network using importance sampling. And the trick is very simple. You use your approximate inference network as a proposal distribution to importance sampling, and then use as weight the ratio of the prior, that's something you can evaluate, times the likelihood, that's something you can evaluate in this precise setting, over the density of the proposal distribution. And that will be asymptotically exact, also provided that the proposal distribution, so inference network, supports covers the support of the actual posterior. Okay. So this is a nice trick, which you should use if you're in this setting. I want to make a comment on that, is that, okay, but in the typical story about SBI, this likelihood function is intractable. So I cannot use this trick. That would be nice if I could. However, something you can still do is to estimate this ratio. Okay, you can estimate the correction factor. And the way to do that, again, is just to use a classifier. Okay, a classifier is basically learning a ratio between two densities. So you can evaluate, you can learn actually this correction factor. And so that means actually the classifier-based diagnostics, which is meant precisely to diagnose the quality of your results. Not only you can use it for diagnosing the correctness of your results, but also as a way to fix the approximation. Okay, but then you will tell me, okay, this classifier is also maybe wrong. It's also approximate. It's not based on the actual likelihood. That's true, but you could repeat this process. And actually, if you repeat that, if you then iterate like this, what you obtain is just a sequential neural ratio estimation algorithm. Okay, so this is just to make connections between things that have been developed a few years ago. Everything is falling well in place together. Okay, next topic, how do you deal with nuisance parameters? So we had a good talk about that by Kyle. My takeaway is that nuisance parameters remain a nuisance. And so he had a slide about that, the curse of dimensionality for nuisance parameters. So when you have a parameterized neural network, which is precisely what we have when you have an inference network, it will be parameterized also by the nuisance parameters, and the interpolation is non-parametric, then that will require many samples for a high-dimensional nuisance parameter space, leading to a curse of dimensionality. So I don't think we have already many good solutions to this problem. Certainly, sequential algorithm may be our way to go on this problem. Kyle mentioned a couple of works in his talk about this, and the basic idea was to use some interpolation, the same use. Yeah, so I know this one, I don't know so much about the other, but this one basically is to, again, use the structure of the problem to extract out the dependence to nuisance parameters out of what the inference network has to produce. So for example, in this case of density ratios, if the dependence, for example, if you have a mixture model, if the dependence is on the coefficients of the mixture, then you can pull that out of the inference network. And this is what we did with Eshik and NJ. Okay, next, and that will be my last takeaway, actually. but I think this one is important because I don't have any answer and I'm not so sure if that's really a problem. So we had this talk by Lily, and she had this slide that basically says that neural density estimators do not know what they do not know. And indeed, when you train a generative model, for example, on MNIST, and then you present to that generative model of MNIST the image of a sock, then it thinks that it's something very plausible under its distribution. That does not make much sense, but this is really what happens. Okay, so we should be cautious about that. And then she told us a story about this in the case of anomaly detection. This morning, we had another talk by Alexander on misspecification. And basically, one of the take-home message was to say that simulators are imperfect, but they are at least good enough. Now, if you combine these two messages together, I'm a bit worried. Because if the simulator is misspecified, then the data, the one we actually collect by the experiment, it may be out of distribution for the inference network. Meaning that the data can be projected maybe anywhere by the inference network. So is that really an issue? I don't know, but I'm a bit worried, okay? There are, I know there is a paper studying a bit this problem in the context of SBI with adversarial examples. They also show that, yes, inference network can be vulnerable to adversarial attacks. And I think this is also related to this problem. Okay, so to summarize my summary, my 10 takeaways. First, SBI is valuable when likelihoods are tractable. Second, unfolding, in my opinion, or one way to attack unfolding is to view it as an aggregation of amortized posteriors. Third, the requirements for accuracy and reliability when it comes to applications, real applications of SBI are really strict and high. Fourth, you should use diagnostic to assess the quality of your approximation. Fifth, to make your inference network better, just build a larger training set if you can. Maybe an infinite training set if you are in this special setting. Consider deeper and larger networks with more parameters and train them for longer. 6, maybe you should think about how to regularize your inference network to, for example, avoid overfitting. 7, if you can, and if you have good reasons to, you should hardcode as much as possible the domain knowledge that you have directly into the architecture of the network. 8, use important sampling if you can evaluate the likelihood. That will help a lot. 9, nuisance parameters, you should consider them, but they remain difficult to properly. They remain very difficult. I mean, they remain an obstacle to their proper treatment because you have to build this huge training set with all configurations of the nuisance parameters. And finally, neural density estimators do not know what they do not know, and maybe that's also an issue for SBI. That's it. Thank you.
Comments, discussion points. Yep. Let's wait for the microphone, I guess.
Thanks for your talk. I had a question. It was relatively early on where you said all these tests only tell you whether or not you've failed, not whether or not you've succeeded in your estimation of the posterior distribution. But I kind of thought in the case where, think of a simple example, I have one parameter, I've some mechanism, I have a machine for generating the posterior distribution, given some data. If I do a coverage test on that parameter, and the coverage test is incredibly high, as in it is not, I've done many tests. Is the coverage test not basically a gold standard for saying the posterior has the correct coverage properties, therefore it is the posterior distribution?
No, there is an easy counterexample to that. If every time the posterior approximation that you should produce is just the prior, will encourage.
Okay, so I suppose in that case, you're also saying there's two different types of failing, right? You're also including failing as being underconfident as well as a failure mode, basically, that your posterior distribution isn't as tight as it could be.
Yes, exactly.
Okay,
Yeah,
okay.
yeah.
This,
Yeah, thanks for the nice, not summary talk. So I had a question on this, like the fact that you can use SBI for like likelihood available situations. So it seems that, okay, we can of course still do like the likelihood free version and do NPE and so on, but then you should be using somehow like this magic power that you still have the likelihood available. So the important sampling is one thing, but even like during the training, I mean, like the original mining gold papers, I mean, okay, so there was like something available like in terms of the joint likelihood and so on. So is there like some kind of conceptualization whether or not you can use during the training this fact that you have the likelihood available in some ways other than maybe like this pre-computation aspect, so like the gradients or the likelihood itself?
Yeah, certainly. So I suppose, for example, if you take the case of normalizing flow, trying to directly estimate the posterior density, usually we do that by just minimizing the KL divergence. But since we know the target, we know exactly the numerical density value that the network should produce. Of course, certainly there is a way, and maybe certainly you should use that as a target directly.
Hi, Gilles. Thanks for the very nice, not summary highlights talk. I was curious about slide 17. You talked about this sequential NRE to, I guess, over multiple iterations make your performance better and better. I was wondering if this is you have any success stories here. At least in my personal experience, this like when a neural network can't capture something, the classifier can't capture the difference either, and then we kind of get stuck.
Yeah, that's an issue. Of course, you need a very strong classifier to pick up this. Maybe you are maybe only wrong in details or in some regions of the data space. Yeah, how do you detect them? And for that, you need certainly a very good classifier, which you need to train also, and certainly also a very large data set. So yeah, it's a trade-off.
But there are examples where like the first time it didn't work, but with the correction it got better, and with another correction it got better. Is that the idea you were trying to, like, or have I misunderstood? What do you mean by sequential NRE?
If you really look at sequential NRE, the algorithm, SNRE, as it's called in some packages, then it's exactly doing that. The next ratio is basically, you can view that as the correction you should do.
Okay, but conceptually it's the same thing. Like okay, cool. Right.
any other questions? We have plenty of time. Oh, there we go.
So thank you for the nice presentation. I'm Marco Letizia from Genova, and not just a small comment as a complementary contribution to this. I think that what's your take on the fact that while maybe you wait 10 days to train your neural network, and whether because the problem that you want to solve allows it, or maybe just because you want to try something fast, maybe what's your take on maybe throwing a linear model at your problem?
So what's your question?
So my question is, what's your take on the fact that while we build complicated models and maybe take 10 days on a GPU to train, and then we might run in all these series of problems that we want to fix, we can also try and throw a linear model, a simple linear regression model, or a simple classifier, or a much faster model, either because we have a good prior on the problem that we want to solve, and maybe a simpler model could work, or maybe because we want just a dirty and quick solution to see what's going on as a practice.
So as long as you are aware that you have an approximation of the actual target posterior, and certainly you are comfortable with this approximation, then that's fine with me. But what I mean is that you should be conscious that, for example, if you use linear SBI, that you don't get the exact.
No, absolutely, absolutely.
So I had a clarifying question on this slide, and then I might have another question if this is quick to answer. So here, like this WI, so this, is it true that this is a function of both the theta and the D? So it's like some kind of a 2D function. So does it matter that it's a 2D function? Like, would you need to like somehow, and I guess it's a high dimensional. So the W is really some kind of a high dimensional function. Does it matter like that it is like that? Like, how do you do this in practice? Like, do you?
It's like in neural rescue estimation, you have a classifier which takes both the data and the parameters. For me, this W is just a classifier, it's the same object.
But would you in practice like estimate as a function, or
Yeah,
it's like
yeah.
sample by sample? Like how would you estimate the W in practice?
So here there is no estimation, you just compute it. You have all the ingredients to evaluate these 3 terms. But when you don't have access to the likelihood, when it's because it's intractable, then you can learn a classifier.
And
That gives you a function that you can evaluate at any theta and x.
And yeah, and that classifier will be a function of both the theta and the x. Yeah, all right, okay, good. Yeah, good. And then the second point I want to make, so the very last takeaway that you had, this is something that I've been also concerned about, and this is actually, I think, a really important point to highlight, especially since I'll also make the point in my talk that people are now starting to use these SPI methods in kind of more kind of classical statistical modeling, actually because of the reason of amortization. And we all know that, like, you know, most statistical models are wrong. I mean, all models are wrong, but some are useful. So we know we are using this for misspecified models. I think it's true probably also, I mean, it's true in physics also, even though you have very fancy models, they're all misspecified. But then especially, you know, in this kind of modern use of these techniques for, you know, this kind of spherical cow type of models, we know we are actually applying these for misspecified models. So your data comes from something that definitely was actually not part of the training. So well, I guess we both share the concern of the robustness of this. Like, do you know, has anybody looked at this? Like, is there any way to somehow robustify this? Like, the nice thing is that if you do classical statistical inference, you have well-known robustness properties. Like MLE has well-known robustness properties under model misspecification. Can we do something like that for SBI?
Yeah, I think the issue comes from the neural network. It's an out of distribution problem. To me, it's not specifically related to SBI. I mean, SBI inherits from this problem, but the core of the problem is the neural network. If you use a neural network on test data, which does not come from the same training, from the same distribution, then who knows what can happen. And this is precisely what this work show. And so all follow-up works that Lily mentioned certainly are things to look at if you want to make SBI more robust or robust to this kind of problems.
Yeah, and I fully agree that like somehow it's a question of robustifying the neural network, but do you know of any way to do like for example, like one thing that came to mind is that like the work that Gaia and others have been doing, they have this weight clipping on a neural network. So could something like that be done to somehow guarantee some kind of robustness for it?
Maybe, I don't know. And then I think we come back to the question of the thing that was mentioned with the anomaly detection. You need to make assumptions about this distribution.
Yeah.
Okay, thanks.
Any other? Two more in the back. Yeah. How about you guys right near the microphone? Oh, you already asked a question. Well, maybe a guy who didn't.
Yeah, just a quick comment to this, let's say ORD with the high dimensional density estimator. So there's a bunch of work in machine learning. I mean, I haven't been recently checking, but then I think the first time they discovered this is like a huge issue actually. So they discovered this in like 2018 probably, in some like when they just were training these large image density estimators. So they discovered this, like the ORD behavior is completely random sometimes. So then, yeah, there's a bunch of follow-up work. So if you want to take a look.
Yeah, I agree. No, this is something which is well known in the machine learning community, but maybe not so much here. This meeting.
Back to
Yeah, maybe just on the previous point. So I mean, on this OOD and question. So one kind of subtle point in particle physics, at least, is so the normal like SBI story goes that the simulator itself has these parameters theta, and we run the simulator forward, and then those are also the theta that we do inference with, and that might be high dimensional and Nugent's parameters. So in high energy physics, actually, that's not the case. So like the Nugent's parameters that we have is they're not somehow like necessarily a knob in the simulator, but it's some kind of effective parameterization that we put in later on. So it's like these parameters that we use to do these interpolations and so on. And so in a way, like what we do implicitly in particle physics is that we kind of what Jesse called like some kind of disentangled low rank reparameterization or something like this. So we use the simulator to kind of get some samples in some space of parameterization, but then we kind of use these samples that we get from the simulator to create a new parameterization that then we believe still is able to capture the actual data, even though there's like no way to kind of tune the simulator to actually generate the data that we observe. And so somehow by this trick, we kind of get around, like in the traditional particle physics setup, we get around this limitation that, I mean, nature might not be Sherpa, but we found like a parameterization where, okay, one parameter setting is going to be Sherpa, and then we believe it's flexible enough to kind of also capture nature. And so maybe kind of some kind of reparameterization there could be useful.
Any other? Otherwise, oh, Rania.
Thanks very much for the nice talk. I'm not sure I followed this discussion entirely just now, but I mean, it's not just a problem for neural networks if they've been trained on data that's not representative of what you're trying to model. So I don't quite understand why this is just a discussion about machine learning rather than a discussion about modeling in general.
Of course, you can fix this problem by making your model more faithful with reality, of course.
Right.
And in this case, when you will train this neural network on training data you've produced with this more realistic model, this problem should vanish. That I agree with. But
so in this particular context is the,
meanwhile,
oh, sorry, yeah.
Meanwhile, I think we still want to do inference with the imperfect model that we have. And I'm just stating the issue that this neural network, they may be picking up on artifacts of the simulations that are not there in reality. So when you will feed real data to the neural network, maybe you will have issues. Maybe.
For sure. Yeah. And no, just for sure, we know our simulation is not perfect and the neural network will pick up on that.
Yeah.
Well, if there's no other, yeah, one last comment from you. Good job.
Thanks again. I just wanted to ask you about the kind of other mode of doing simulation-based inference. So we do it in the dark energy survey, or the galaxy surveys do it, and it seems to be what's popular in at least cosmology, which is this two-step process of learning a compression of the data, which you can think of as an embedding, if you want, and then learning the likelihood using density estimation. And it seems to be quite different in flavor, at least this way mindset of doing the compression first. I at least think it kind of makes things more robust and you can see what's going on. But I wonder what your view on this kind of way of doing it is.
Yeah, I have actually the opposite view. I've never understood why there was a distinction in the papers, because the neural network will have to learn a compression. If you just take any intermediate layer inside the neural network, it's a summary statistic of the data. That's it.
I suppose because you can do validation on the compressed statistic and then learn your density on a different training set.
Sure.
So you can split it up. And also you can do likelihood estimation rather than posterior estimation.
Yeah. If you take, for example, all the papers on NRE, you learn at the end of the final output of the classifier is something that you can reformulate as a likelihood ratio. That's a summary statistic. conceptually, to me, they're the same thing.
Okay.
Great, so I think we have this, move to the next speaker, so thanks.
So the back need to find seats, you help find the seats? There's plenty of room up here. 30 minutes, so I'll give you 5 minutes. So our next speaker is Mikhail Kuselny. You might remember him from the morning, and it's from Carnegie Mellon. He's going to give the highlights on the statistical perspective.
All right, thank you very much. Yeah, so I'm back. So now we are going to kind of talk about sort of more kind of high level thoughts on this meeting. So kind of first to give you the plan here. So I'll be making some remarks on selected topics from this conference. These are kind of the thoughts I more or less had on my mind, at the end of these couple of days. So I'll be saying something about interpretability, something about model agnostic searches and anomaly detection, something about unfolding, generative models, and simulation-based inference. And so I should make the disclaimer here, first of all, that I'm not trying to cover everything. That's not exhaustive by any means. And also the way I've been approaching this sort of summary or highlight talks is that I'm kind of more trying to kind of give my thoughts on things, or like what I had as kind of some thoughts or extra discussion points or extra context based on things we have seen. So this is not trying to be a review of the talks. I'm not going to try to repeat the talks we have already seen. I'm trying to maybe add a bit more extra context to those talks. So that's the plan. We'll see how it goes. So we'll start with the first topic, so interpretability. So we had this really nice talk by Jesse on the kind of the high level kind of questions surrounding interpretability, and he kind of more or less started with this question of what is interpretability and why do we need it. And there's this amazing quote that he made at some point during the discussion. There is this warm, fuzzy feeling that you understand what your neural network is doing. I think that captures really the essence of it. Of course, we can try to formalize this, but really, I guess that's what we are aiming for. I guess in this workshop, that's what interpretability means. Because, I mean, clearly, there's not a unique definition of interpretability. It means different things in different contexts, but I guess always gives us this warm, fuzzy feeling. All right. So Jesse shared his view on interpretability, and earlier today, we heard from Tobias more also about this. And I think we're all kind of on the same page with interpretability, which is sort of this question, like, do we actually really need it? Like, do we always need it? And just to kind of give you maybe one sort of a thought exercise here is that, imagine that you're in some more classical situation. You have just some parametric statistical model. Just say it's a very complicated model, some, really complex model someone has cooked up. And then you go ahead and you find the MLE under this model. And let's say you can do it, maybe put it on Mathematica and it spits out some, crazy complicated closed form expression, but you can do it. So usually we are happy at that point. Like I usually if we can find the MLE, we have a closed form expression for it. Usually we are quite happy because we have a lot of faith in the MLE. Like we know a lot of nice properties for MLEs. We know that they're generally speaking behave well. So at that point, we usually don't start asking interpretability questions. We don't start like interrogating this formula for what is it that you're seeing in your data. We just kind of go with the formula and we are happy. So I think it's a little bit the same with these machine learning methods that like we don't necessarily always need even if we cannot interpret or kind of like understand actually what the machine is doing, or in this example what the formula is doing, like maybe we don't always need to be able to interpret it. And so Jesse made this point, and this has come up in many other places, that like often we kind of know similarly what these machine learning models are really ultimately trying to do, at least asymptotically. You just look at the loss function and see like what is the kind of the functional, like you look at the functional derivative of the loss function, set that to 0 and see what comes out. And so usually you know that you're at least trying to approximate something like the class probability, likelihood ratios, the score, or conditional mean, and so forth, depending on what loss you have picked. So as long as you can sort of validate that you're roughly speaking getting that, and the neural network is not doing anything crazy, like, do we actually really need interpretability? I think that is sort of like Jesse's point. I think also Tobias's point, and that's also I kind of share this view. So I think it's not always needed. At the same time, I think there are clear use cases where you do need it. And so this morning I talked about the model independent search, there we would very much like to understand what is the neural network seeing. So I think there are use cases, and I think the ice cube example was also a great example of that. So I think there are use cases where we really do want to understand what the network is doing. But if you are using neural networks for some like a particle reconstruction or jet classification and so forth, like do we really need to be able to interpret it if it works? And you can kind of it's pretty high, you have if you can build this high trust in the network, otherwise maybe we don't need to be able to interpret as humans. All right, so then sort of another question I want to raise here is like overall, like, okay, so if we decide we need interpretability, like how realistic is this really? And I think it's useful to kind of think back, like what is the simplest possible model where we might want to ask these questions? And I think this is linear regression, which also like Jesse's most underutilized machine learning model. And it's important to highlight, like, interpretability is really hard even in linear regression. So anybody who has ever taken full semester long regression course or has taught one knows that we go over all these different procedures for like kind of judging the statistical significance of these betas and model selection of these betas, like should the betas be in the model or not. And that gets very complicated very quickly because it actually depends on what order you look at the betas. It depends on whether you're adding them to the model or removing them from the model. Do you do it like in groups or one at a time and so forth? So this is very difficult even in linear regression models. And especially if you start to put like interactions to the model, then it gets very messy very quickly. So this is very difficult even in the simplest possible models. If it's difficult in linear regression, like, do we really like expect to be able to solve this in like a the more complicated regression model like a neural network or something along those lines? So it's kind of worthwhile to be maybe a little bit realistic in terms of what we can expect to see here. But still, okay, like linear regression models are usually considered as interpretable, regarded as interpretable models. We at least we maybe get more of this warm fuzzy feeling with this linear regression models that like we know what is going on. So one thing I want to point out here, or maybe make a suggestion, is that there are these nice middle grounds between like linear regression and then these totally black box neural network type of models. And especially, it's maybe worthwhile to highlight this idea of additive models. And there's some really great expertise here in UK on additive models. Some of the key experts are here. So so additive models are models like this, where you generalize linear regression a little bit by saying that I basically write my response as a linear combination of functions of the individual covariance. The key point here is that these functions are allowed to have some flexible structure. So typically these functions would be splines. So these would be some nonlinear functions that you learn from the data. But the nice thing is that since it has this additive structure, you can look at those individual functions and then try to understand how that particular covariance is affecting your response. And you can have also here like interactions and so forth, as long as you sort of keep the complexity under control. You more or less have an interpretable model that you hopefully can at least try to interpret. So maybe a thing to suggest here, and I'm sure someone has done this probably before, but if you have a neural network that you have fitted, maybe it's worthwhile to try to fit some like an additive model or some more interpretable model to that neural network, and see if we can use that to interpret the complicated neural network that we otherwise might not be able to interpret. So might be a good idea. I haven't tried this in practice. I'm sure someone has done something like this. So yeah, so it's good to keep in mind that we have this nice potential middle ground in this spectrum of interpretable models. All right. One more thing I want to say about interpretability is the one thing to keep in mind, which I think has not been raised really, is that really all of these interpretability methods, if we don't have controlled or randomized experiments, they are really looking at correlations and not necessarily causal effects. So anybody who has taken like a stats 101 course knows that correlation and causation are not the same thing. And if you don't have a controlled experiment, you're really looking at correlations. So one thing I want to mention here is that there's this whole subfield of statistics called causal inference, which is trying to figure out, do we have actually causal connection? And we had a very nice talk during this workshop on one aspect of causal inference. So I was very happy to see it because I've been kind of thinking like, are there use cases for causal inference in physics? And we saw one, but more generally, it's maybe worthwhile to consider whether causal inference can say something about interpretability, because if you have a cause-effect relationship that you can rigorously establish, that is something you can interpret. Now you have learned something that I think is interpretable. So maybe a suggestion for Louis and Olaf is that maybe this could be a potential topic for a future PHYSTAT seminar. All right, so that's what I want to say about interpretability. So now the next topic is model independent searches. So this slide we have already seen before. We saw this morning. I'm just putting it up here to remind you of the notation. So overall in Heinz physics, what we are looking for are usually bumps over a background. So we think of our data as potentially coming from this kind of mixture model. We have, there's some background distribution, there's some signal distribution, and we are trying to figure out whether the mixing coefficient is 0 or not. So I talked about one aspect of model independent searches. We've heard also other talks on that. So in all of those talks, the idea is that, so if you have a good idea of what PB is and what PS is, then this is a very well studied problem. This is the model dependent version of the problem. The model independent, or more generally model agnostic version of this is when you start to relax your assumptions about the PB and PS, the background distribution and the signal distribution, as you design your test. So you want to design a test that is not necessarily making a strong assumption of one or the other or both. And one thing that is important to highlight is that it's not like an on or off, like it's not like a black and white. It's a spectrum of things. There's a spectrum of different levels of model agnostic or model independence. And I think it's actually helpful to put it on this kind of a cartoon. So here on the x-axis, we have the sort of the strength of the assumption we make about the signal. On the y-axis, we have the strength of the assumptions we make about the background. And so in this corner, this is where we have our traditional search methods. This is where the model dependent methods live. And there's maybe a little bit of kind of a sort of space around here because we know how to build in things like nuisance parameters. So you're not making a point assumption about your background signal. You might have a bit of sort of fluff around with nuisance parameters and stuff. So, but what these model agnostic methods are trying to do is to move away from that corner to different parts of this plane. And so most of the talks we've heard about model independent search, including what I was talking about this morning, they're in this corner. They're basically, you still make very strong assumptions about the background, but you're trying to relax the signal assumption. In fact, you more or less go all the way here because of the sort of the asymmetry between the null and the alternative. So basically, this is a corner where a lot has happened. Also, Gaia's and Margot's work is, I believe, in this corner. This corner is kind of more the direction where if you don't trust your background model, if you need to get some of a data-driven background, we've done some work on that, and of course many others also. So this is kind of the area where you still kind of have a good idea of your signal, but you're trying to relax your background assumption. So that, I think that is model agnostic. It's just model agnostic for the background. But then the really interesting direction is that how do we go this space? Like how do you go? Because of course the issue with, for example, what I was talking about this morning is that we are still making a very strong assumption about the background. And I mean, we all know that it's actually not true. So how do you move to this direction? And for example, what Gaia talked about is that they are adding these nuisance parameters to the background model. So they are kind of moving, they're pushing it this way. So I think this is a good way of thinking about this. And I encourage everybody who works in this area to think like your method would lie in this plane. I think it's helpful to try to kind of, keep the discussion sort of, focused, or it will be helpful, I think, for the discussion overall. So at least for me, this is helping my thinking to think about it in terms of this plane. Okay, so I want to make a couple of connections here between what we've seen about model independent searches and kind of more bigger picture. So I want to highlight that these model agnostic search problems, these do relate to many problems that we are quite familiar with in statistics. So for example, the version of the problem I talked about this morning, can also be understood as a two-sample testing problem. So you have two samples, one comes from P1 and another one comes from P2, distributions P1 and P2, and you're trying to understand, are they the same distribution or not? That's your null. So that is what is called a two-sample testing problem. In fact, what I talked about this morning is exactly this problem. Also, Gaia's and Marco's work, I believe, can be understood this way. So, so that's a helpful connection to have. Another more or less equivalent kind of connection here is that most of these methods can be understood as what are called collective anomaly detection methods. So that's why anomaly detection comes up as a term in this context. You're looking for anomalies, but it's very important to understand that what you're looking for is what's called collective anomaly, where it's a collection of data points that together define the anomaly. And that brings up the kind of what I really want to highlight here, which I think is a really key point to understand, is that these small agnostic search methods are not usually outlier detection methods. Like usually you don't expect your new physics to be in the tails, like out of distribution. Of course, if you see that, then great, that's maybe interesting, or probably is interesting, but usually that's not what is expected to happen. Like you're really expecting bumps on top of background. I mean, more or less along, like something like this. This is not in the tails. This is not an outlier. Like nothing here is an outlier. Any point, any data point you pick here is going to look exactly as any normal data from the background. Like point by point, you cannot tell them apart. The only reason you can tell them apart is that there's a collection of points here that together form the anomaly. So oftentimes, there's this confusion that, because anomaly detection for many people is outlier detection, but in particle physics context, the relevant type of anomaly detection is collective anomaly detection. That is not the same as outlier detection. All right. So then going back to this figure, so what I want to briefly highlight a very recent paper that we just put out, this morning. It's an archive since this morning. We are going to this direction now. So I talked about the previous work we done here, where we make strong assumptions about the background. But of course, this is a bit of a concern that we don't really trust the background. So with a student and a collaborator at CMU, we basically asked, okay, how do we move here? Like, how do we go here? So I want to just briefly highlight this because I think it's a really quite interesting new idea. So this is the archive number since this morning, and so the idea here is that this is a very short note that we put together from something else, but we put it on the archive at the same time. So so the idea here, so that we started from the idea. So this figure here shows like a nice cartoon to explain the key idea here. So we started with the idea that my collaborator at CMU, he's interested in looking for new physics in the 4B channel. So there's some kind of a background in your 4B channel, and there's maybe a signal bump in there. And what we know is that there is this nearby 3B channel, so 3B channel, that is kinematically similar but not the same. And we don't expect necessarily signals to show up in 3B channel. So if we define that we're only looking for signals in the 4B channel, then 3B is free of signal. The classical signal that appears here is the di-Higgs signal, but also you might have some exotic resonances that would decay to 4B quarks, and you would not see them in 3B channel to some extent. So basically the idea was that, okay, what if we look at basically the density ratio between the 3B and 4B samples? We know that the backgrounds are not exactly the same, so we don't expect this to be an identity line. So even in places where there are no signals, the density ratio, here's the density ratio, it's not going to be 1, but it's going to be like some kind of a very well-behaved smooth function. And then where you have a signal, you would see a bump. So there would the signal would show up as sort of a high frequency bump in this kind of background of low frequency stuff. So the idea here is, okay, so how do we look for such bumps? And we want to do this in a high dimensional space. So this is a 1D cartoon to explain the idea, but we want to do this in high dimensions. So then the idea is that, okay, well, how do you go about looking for high bumps in a high dimensional space? Not in 1D space, but high dimensional space. And the idea was that, okay, well, these bumps, they are basically high frequency features. So if we apply some kind of a low pass filter, we should remove any bumps. And we realized that it's actually very easy to apply a low pass filter to your data. You just smear your data. You just add noise to your data. You take your data points, add some noise. So the effect of that is that you're actually convolving these densities. And what happens is that the low pass filter is going to especially kind of hit the bump here. So the bump is gone, but the rest is more or less the same. It changes a little bit, but not much. And now if you now look at the density ratio here, here's the density ratio. The bump is gone. The rest has changed a little bit, but not that much. So now if you compare these two and look at the ratio difference, that should localize the bump. So this is now the difference in those two density ratios. And that's, you can see here that the bump has really been amplified. So that was the key idea. And the nice thing is that all of this can be done in high dimensions with the help of neural networks, because we are very good at estimating density ratios using neural networks. So what we do in practice, what we show in this node is that when we do this for the Dye-Higgs signal, this is actually able to localize that in a 16-dimensional space. So basically, you train these density ratios using you learn them using neural networks. And the cool thing is that you never need to compute this convolution explicitly. You just smear your data, and then you train a network between these smeared samples, and you basically learn the density ratio of the convoluted densities. And that seems to localize. That seems to work for the Dye-Higgs signal, and I'm quite excited about this idea, because I think it's quite potentially powerful and seems to kind of use the good sides of kind of smearing and neural networks in a potentially useful way. So anyways, if you have any thoughts on this, I'll be happy to talk more about this and hear your thoughts. All right, so we'll move on. Okay, so that was the end of the model independent, model agnostic search part. So now I'll have one slide about unfolding. So unfolding, this is more just a kind of a summary of where things are, what I see as sort of exciting new developments in unfolding, which we have heard about during this workshop. So I think a big development in unfolding in the past few years has been the use of machine learning, as we have heard in this workshop. So there's just been two ways to do it, which has been highlighted in many other talks. So there's the omnifold approach, and then there's the generative unfolding. So one sentence summary of what omnifold does is that it does this iterative reweighting at the smeared level, and then it does this the magical step 2, right? You pull the weights back to the particle level, and then you smear, well, not smear, but to kind of make the weights consistent at that level, and then you iteratively proceed. That can be shown to be the same as the EM algorithm in the limit of doing exact density ratios, basically. And then we have the generative unfolding, which is using actually the idea that Jill just talked about. So you basically get these conditional probabilities of going back from the smeared space to a true space. You sample from those, and then you get a better estimate of what happens in the truth space, and then you iterate. You have this new estimate. Then based on that, you retrain for these conditional generative models, and you keep going. Well, you heard talks about this, so maybe I don't need to explain that in more detail. Anyway, so these are the two ways to do it. So why is this interesting? So it's interesting because these methods have a lot of benefits. So first of all, no binning required. So it's a binning free approach. It gives you unfolded results at event level. So basically, at least in omnifold, you basically get event level weights. In generative unfold, maybe something a bit different, but still you get event level information. These work in high dimensional, or at least moderately high dimensional spaces. So now we can do unfolding with more than just one variable or more than a handful of variables. But for me, actually, the most interesting thing is that these actually don't require an explicit model, explicit forward model. Like in classical unfolding, you always start with the response matrix, right? And actually, you don't really know the response matrix. You need to estimate from the data. So we have some other related work that shows that's actually kind of surprisingly difficult, has some unexpected consequences. So the interesting thing about these methods, they never need this explicit sort of forward model. They sort of, in some sense, like implicitly reconstructed during the unfolding, which is kind of interesting. So I find this last point quite interesting. But to me, really the big open question in all of this is that ultimately unfolding is an ill-posed inverse problem. If you really truly were able to get the MLE, for example, it would blow up. It should blow up. It's an ill-posed problem. It should look terrible. The data doesn't have that level of information. So somewhere there's regularization going on. I mean, these are regularized estimators, no matter how you look at it. But the question is, like, where is that regularization? Like, can we characterize that regularization? And that seems kind of complicated. So we are working on this and trying to understand this in a bit more detail. But right now, my thinking on this is that what is probably going on is that, like, all of these neural networks that are part of this, they are implicitly regularizing the problem. So basically, by the structure of the neural network and the training of the neural networks, That's where the regularization is. Like for example, omnifold, it usually seems to converge actually in relatively small number of iterations. So it's not so much regularized by the number of iterations you take. It seems to be more regularized by how you train the neural networks and what neural networks you're using. So there is something going on. I mean, so this is important to understand because this will affect the the biases that these estimators might have. So yeah, so we are trying to understand this, but it's a very non-trivial problem. So we'll see what we can say about that. All right, so that's the one thing I want to say, or one slide I want to show you about unfolding. So we will move on. So okay, so the next thing I want to briefly comment on is generative models. So there's been a lot of discussion about generative models in this workshop. So I want to make a couple of remarks. So the first one is just like, I like this figure a lot. I put it in here because I like this very much, because in one figure, it sort of like shows like the current kind of state of the art of generative models. So like for me, as someone who only recently has been looking at this, like I found it very helpful to see it all like side by side like this. As far as I understand, it comes from this blog post, which is actually a very useful recommend reading on diffusion models. So this shows that basically all of these methods in some sense share a similarity, which is that in all of these methods, there's this latent variable z that comes from some simple distribution. Usually it's just standard Gaussian. And then there's some neural mapping that takes this z one way or the other to a data level random variable. Like an easy example of this is in a generative adversarial networks, right? Where you start with noise, you have a network to map this to data, and the way you train it is you have this sort of adversarial training going on. So that was, I think, one of the first methods or neural methods for doing this kind of stuff. Then of course came the VAEs, but the modern stuff seems to be the flow-based approaches and diffusion models. I mean, this has been pointed out by many people. These are the ones that seem to work best in practice. My take on like what seems to be the pros and cons between these two, as far as I understand, with flow-based models, if you need densities, then this is very good for that. But then if you need performance without densities, then diffusion model seems to be the way to go. So we are looking at diffusion models in some different contexts, and it's been a very educational experience to learn how this works. But the basic idea in diffusion models, you've heard many times already, right? Is that you take your data, you add a bit of Gaussian noise step by step until you just have white noise, and then you try to reverse this. And this can be formalized using stochastic differential equations. So there's a rigorous mathematical theory behind this. So we actually kind of understand what these are doing. I don't think we understand why they work so well, but we understand what they are doing. And it's nice because then you can start to build an extra step like conditioning and other features into these models. So it seems like a very I mean, it's a useful kind of tool, and it works well in practice, right? Okay, so there has been a lot of discussion about these generative models. So I thought it might be helpful to maybe summarize this discussion a little bit, especially since I think we are kind of learning something here. I think that discussion has been converged. I think there's a lot of agreement in the room about some of these points that have been raised, including some of the preferred questions that were put on the PHYSTAT page. So I thought I'll give my take on this. We can maybe then hear from others what others think. But my take on some of these discussion points is that, so one of the points that has been brought up both by Louis and also Jesse also brought this up already a few years ago, is that, okay, so if you have a generative model that's trained using n data points, and then you use this to sample more than n data points, you sample some m data points where m is greater than n, did you actually gain anything? And I just learned that this is called gamplification. So the agreement seems to be sort of a cautious yes, but with a sort of a caveat. So of course, if you have n data points, you have n data points. That's the information you have. So if you gain anything, it has the extra information needs to come from somewhere else. And where it comes from is that, I mean, basically these neural networks or whatever neural method you use or machine learning method you use, they have inductive biases. They're implicit in the models. These are not very sort of explicit, biases, but they're there. That's why they work. So it's those inductive biases that sort of would potentially kind of help you produce a useful larger sample based on a smaller sample. but only if those inductive biases, of course, are accurate, like if they reflect the reality. The issue here, of course, that it's very difficult to characterize what those inductive biases are. Like, if you have some classical kind of a regularized regression, right? You have like the penalty term, it's very explicit what is going on. With these neural methods, it's very implicit, but it's there. And it's that sort of that regularization that is like ultimately making these things useful. So here also, I think it's useful to just go back to the simplest possible model where, we can have a discussion about this. And to me, that is a kernel density estimator. This is, of course, not a neural generative model, but I think it's still conceptually useful to think about this. So here's a plot I generated in R. I sampled, 10 data points, and then I put a estimated kernel density estimator based on this. So now you could balance use this as a generative model, right? You could sample from this PDF and produce, this is 10 data points, you could produce 100 data points. And the question is that a useful thing to do or not? And I think the answer is exactly like, this kernel density estimator is basically making some assumption about the smoothness of the underlying PDF. To the extent that those assumptions are true, yes, you will gain from doing this. Like that is that those 100 points you sample are more useful than the original 10, but only if those assumptions are true. Like, what if this actually came from some kind of a uniform? These 10 points could come from a uniform distribution. I actually generated this from standard Gaussian. So this is pretty close to standard Gaussian, not exactly standard Gaussian though. So this is already a little bit wrong. But these could have come also from maybe a uniform distribution between -2 and 2. And of course, in that case, this would be very wrong. So, the inductive bias could be correct, could be wrong. And unfortunately, it's very difficult to check. But I think this is like useful for like kind of sort of anchoring the thinking a little bit. Like if the sort of the inductive biases in the generative model reflect the reality, then this is a useful thing to do. But if they don't, then you might get badly wrong things. For example, these tails could be very badly wrong if you have something else underlying this standard Gaussian, for example. All right, so then another thing that has been discussed a lot is how do you quantify the answer in these generative models? And I had to kind of like think about this hard, and I'm still not 100% like sort of settled on this, but currently my thinking is that so there's like two different types of uncertainties involved. So these are based on data. So clearly there is an algorithmic uncertainty from the randomness in the data, but then we of course have this inductive bias. And this is maybe best understood as an epistemic uncertainty. So maybe a good way to think about this is in terms of some kind of a combination of algorithmic and epistemic uncertainty. And what has been suggested as a potential solution are these Bayesian neural networks. So these potentially are able to characterize both of those sources, but of course with the caveat that you need to be careful to interpret what that answer means. It doesn't have a fully frequentist meaning. It would be some kind of a combination of frequentist and Bayesian uncertainty. And again, like I think the kernel density estimator is a helpful tool here to think about. So of course there are ways to put confidence bands around a KDE. Like there's very well established ways of doing that. Unfortunately, the issue in all of those methods is that they don't really characterize the bias. They characterize the variability of these estimators. So they characterize sort of the algorithmic uncertainty, but not the epistemic uncertainty, not the bias. And and it's very difficult to account for that bias. One thing you could do is like some kind of a non-parametric Bayes approach here, and that would be, I think, equivalent to this Bayesian neural network. So if you're fine with an Bayesian non-parametrics in this case, then I think these Bayesian neural networks are also fine in sort of the more complicated situation. So then another point that has been raised a lot is how do you validate these generative models? And the solution that I think kind of everybody is highlighting, everybody seems to be quite happy about is to train a classifier to separate between the generative data and the training data. This has been brought up in basically all the talks. This is also something we've been doing in various situations. It works really nicely, but it's just important to keep in mind there that what you're really doing is a high dimensional 2-sample test. And there are these well-known impossibility results that like in this kind of non-parametric testing situation, there does not exist a test that basically puts high power against all possible alternatives. So these classifier-based tests, they are going to put power against some alternatives, but first of all, it's quite difficult to characterize what alternatives it has power for. And then maybe more importantly, it's difficult to characterize what alternatives these tests do not have power for. So this is sort of Chill's point, which is that like if this kind of a test fails, you know that you got things wrong. If it doesn't fail, that doesn't necessarily tell you that the model is correct. So, but I mean, as has been pointed out, it's very difficult. I mean, you can never be sure that it's 100% correct, but you can always invalidate these models. One thing that I think actually has not been mentioned, unless I missed it, is that in these alternative models, oftentimes you want to do conditional alternative models, and validating those conditional alternative models is not trivial because you often don't have access to the underlying conditional distributions or conditional samples. So I want to highlight this talk. This is from the PHYSTAT SBI meeting, which has been mentioned many times already. There's this really amazing talk by Julia Linhart on an approach that seems very attractive for kind of validating conditional alternative models. And it's basically based on a classifier, but the key point is that you basically train the classifier without needing access to the ground truth conditional distribution. You basically train a classifier between the sort of the joint distribution and then the sort of the marginal, the conditional distribution, the very sort of in some sense like sample from the prior at the same time. Okay, I should not try to make I will not try to make justice for this because there are people who are more experts on this, but this seemed very interesting to me, and you can look up the details from this talk and from Julia's paper if you are in the situation where you need to validate conditional alternative models. We are looking at this actually because I found this actually very, very interesting. All right, and then the final point I want to touch on is simulation-based inference. So we just had a nice summary talk about simulation-based inference. So I'll just add a few more things to that. So okay, so the high-level point, of course, in SBI is that you have a parametric model where your model is only available as a simulator. So what you have a sample of parameters from some prior distribution. For each of those, you have access to a sample from the model. Then you also have observations, and your task is to use those observations and these samples to do inference, meaning you want to do things like point estimates, confidence sets, creditable sets, and so forth. And the key insight, which has been again brought up many times, is that with machine learning, you can now do these things for very high dimensional X, for very high dimensional data sets. You can do this. So there was a couple of interesting discussion items that came up during the talks on this. This is actually a question I raised, but this brought up some interesting discussions during the reception last night. So I thought I'll mention it here. So I made this point that likelihood ratios are not guaranteed to be optimal test statistics when you have a simple versus composite. And when you're doing Neumann inversions, you're really doing simple versus composite hypothesis testing. So there's no guarantee that likelihood ratio is going to give you the smallest possible confidence sets. So the question is, are there other test statistics you might want to consider? And I want to highlight this work from CMU. So I was part of this work, but this is really led by my colleague Anne Lee and her group. Luca Macerano was the student who led this. So we call this Voldo. And the idea was to use a test statistic like this, which is a little bit similar to the Volt test statistic, but for basic conditional means and conditional variances. So what we have in here, we have basically like how much does your conditional mean differ from your null, and then sort of normalized by the covariance of your basically conditional distribution of the parameter. So why could something like this be interesting? So there's two reasons. The first reason is that many neural networks already give you estimates of the conditional means and conditional variances. I mean, basically, if you ever have a neural network that you give like some high dimensional input and you train it to output some low dimensional quantity, which is, for example, in hydrogen physics, I think this is used a lot for particle reconstruction. You have a neural network where you take some, detector readouts and you make it give you an energy or something like that as an output. If a network is trained like that, it's really getting the conditional mean. Similarly, in astrophysics, I've seen work where people would take some images and trying to make a network predict the mass of a galaxy. So those networks are always learning conditional means, and it's actually very easy to generalize those to learn the conditional variance. So this should be really understood as Bayesian posterior mean and posterior variance. And if you somehow try to use this to get a credible set, that would not be a frequentist confidence set. This would not have a coverage guarantee. But what you can do is that you can still build a test statistic based on those. I mean, you're free to use any test statistic, but based on this, you can build this Voldo test statistic, and then you can apply Neumann inversion. So that is the idea in this Boldo. So, and that's what the idea in this flowchart here. You have a test statistic that involves these two quantities. You do Neumann inversion to invert that test. In order to do that, you need to know the null distribution. So there is this quantile regression step to get the null distribution of the test statistic, which you can use, again, you can do this based on the simulations only. And then you invert that and you get a frequentist confidence set that by construction has correct coverage because it's based on Neumann inversion. And that has potential benefits, first of all, in the sense that you don't really need to think about your neural network architecture because you already have networks that give you this. But then interesting, and this is something we discussed last night with a group of people, is that this also allows you to leverage prior information in the sense that these are really Bayesian quantities. So there's a prior. The prior is the distribution you use to sample your thetas. So if you have a well-specified prior, this is going to concentrate these confidence sets and make them smaller than you would have with a flat prior, for example. So if you have a well-specified prior around wherever the truth is, it's going to make your set small and more efficient. But at the same time, if the prior is misspecified so that the truth is somewhere else, you're not going to lose validity. This is still going to give you valid frequentist confidence sets. They just might be larger than what is optimal. So, so this is potentially interesting, and there might be use cases for this in both in astrophysics and particle physics. All right, and then the very last thing I want to mention, so this was David's question during the SBI talk, was I think it was more or less like this: is there a more general notion of SBI with like models with tractable likelihoods or just statistical models more generally? And the answer is yes. So this is something I'm very excited about these days. So there's this very recent important development happening in statistics where people are starting to use these SBI methods in more classical statistical modeling contexts. And this is especially happening in spatial statistics. We're very often in this situation where our models are just very slow to compute, like we just cannot do the computations. So we need something that is faster, even though in many of these cases, we do know how to do the likelihood computations. Like for example, for a Gaussian process, we know how to do likelihood computations, it's just very slow. So many people, us included, have realized that you can actually use SBI. Also in this context, is sometimes called neural inference, or the more really the driving force of all of this is that these are amortized inference techniques. And this has huge benefits, at least in spatial statistics, but I believe also more generally. And so this is a very nice demonstration of what you can do with these things. So what is happening, this is too small for you to see, but what is happening here is that the globe is divided into small patches, small regions. And in each of those small regions, you're fitting a stationary Gaussian approach model to some satellite observations. And that would be slow to do using classical methods, because in each box, you would need to solve a complicated numerical maximum likelihood problem. And you would need to do it for each box separately because it's not amortized. So what these people did, they showed that you train one of these neural estimators to produce these amortized estimators of your parameters. Once the network is trained, because it's amortized, you can apply it basically for free across all of these boxes, and it takes just a matter of seconds. So basically, they show that you can scale these things up by like many orders of magnitude. So especially in this kind of problems where you need to repeat the same statistical fitting problem, parameter estimation problem many times, you have the same family of parametric models that you need to fit many times, which especially happens with this kind of local moving window type of methods. These are super interesting and attractive methods. And for statisticians, there has been many sessions about this at recent JSMs, and I think I expect to see more of this. I think it's one of the more exciting things happening in statistics in recent times. Okay, that's the last slide. So I'll finish here, and I'm happy to take any questions. Thank you.
Okay, I think we have maybe a couple questions, and then we can continue the discussion during coffee break. Any questions, comments? Yep.
Don't worry, I'm heading to the airport, so this will be the last time I speak. I like to argue that interpretability is really important for things that matter in the field. So for low stakes stuff, fine. But we doing a lot of searches at the LIC where we're training these machine learning things on simulation. And as people know, they're not finding anything, so fine, we can publish upper limits. It's not a big issue. But especially maybe the point I often make that maybe is new to the young people, if you look back over all the putative discoveries in the last decades, the attention immediately shifts. Before you have that discovery, this is on the issue of systematics and nuisance parameters, you're writing them down and you're forward propagating them, and then that uncertainty gets propagated at the end result. As soon as you have a surprise, the whole attention completely shifts. The discussion is all about what do I have to change in order to make this effect go away. So like with the dark energy, the supernovas, it was gray dust. It's a gray dust. The supernovas depend on how old the galaxy is. And these were not systematics that were propagated for. There's new ideas that were, well, maybe they're older. And with everybody knows about PHYSTAT too, but with the Higgs boson anyway, any discovery, you're going to want to know what's going on. And if it turns out that it's the transverse momentum of the seventh jet in the event, that's what they're using to distinguish signal from background, well, all our quantum chromodynamics simulators are truncating a power series, the perturbative series, after just a few terms, and they're almost certainly wrong, the transverse momentum of the seventh jet. So I think our students need to be trained to think about what if I have a discovery, instead of just how am I going to set an upper limit, and be ready to know what their neural net is doing, which I can tell you in CMS, often they don't, unfortunately. Thanks.
Yeah, and I think the reason why they're not doing it right is because it's very, very difficult. So that's the challenge.
Developing those tools and advertising them, making them standard, be great.
Yeah, I mean, I guess the point is that those tools don't really exist. I mean, we've seen some examples of those tools, but
Fuck, today I would apply it when you know the signal as well. No reason to apply
Yeah.
that work you showed earlier
Yeah.
today when you don't know.
Yeah. Yeah.
One more question over here.
Thanks for the summary. I'm curious about the paper you published today, and it's sort of high frequency feature detection. Does this rely on the feature appearing in one specific observable that you feed into? So you're talking about 16 dimensions or something here. So does this rely on the feature appearing in one of these dimensions?
no, it does not. That's the key point. This we are not doing some kind of a low dimensional projection. This is done with a high dimensional space. So this would work with like if you have a bump that is in multiple variables. So that is really the thinking here. Is that because like of course 1D bump hunts have been done for a long time, and I'm sure someone has done some kind of a search of like the optimal direction for finding a bump. But the point is that what if you have a bump over multiple dimensions? Like how do you find such things? And that's my interpretation of what this is doing.
So does it okay? So the bump could be localized in the 16-dimensional space, but could it also be that the bump is localized in something that's sort of a function of these 16 variables, which I think is not necessarily the same thing.
And it probably would be, right? Because if you, I mean, if you were somehow able to find the sufficient statistic for some kind of an optimal test of that bump, so yes, that certainly would probably localize it. But then the problem is that if you have a high dimensional space, that's non-trivial to do, especially if you don't know what the signal is that you're looking for. Of course, again, if you knew the signal, you could train a classifier and then you would find the bump. The issue is that when you don't know what you're looking for, so there was no assumption about what the signal looks like or where it is. I mean, the way we see it is this is a way of finding data-driven signal regions. So the thing we haven't done yet is then how do you then go from that to do the actual test? But what we show is that it's able to localize regions in high dimensional space that are enriched in signal. So we think of this as finding signal regions, and then you figure out how you do some kind of a extrapolation of the background from the sideband to a signal region. That's what we are thinking here.
Okay, thanks.
And one last question from Rania. We can continue discussions over coffee.
It's actually not a comment, and I guess it's not a comment you made, but it triggered me this thing about, somebody said interpretability is a warm and fuzzy feeling. Interpretability is at the heart of the scientific method, right? And I don't think it's just a question for machine learning models. It's a question for modeling in general. What matters is not why a neural network has learned particular patterns of weights and biases, but what information it has learned. And I think it's really important to understand that information.
Well, I might just add that, just a thought that, it's probably not new, but interpretability and robustness go hand in hand because, for example, you give the example of the MLE, which is some messy function. But, just for example, for the MLE for say a Gaussian distribution for the mean parameter would be the sample mean, but you can bustify that by replacing with the median. Here I've understood something and I've figured out how to make my estimator more robust by understanding what's going on, interpreting essentially the MLE. So,
But similarly, you could probably make like a neural network learn the posterior median, for example, so, yeah.
okay, I think we're out of time.
Okay, okay.
Thank you.
Come back for, sorry to reduce.
How do we know if people are coming back?
I think Rob will usher everyone here again.
Okay, so we wait till at least Rob is in, and then
Yeah.
we assume that that means the
Yes.
coffee break was over.
Yeah. So we'll probably give them a couple more minutes, I guess.
Sounds like a plan.
Louise. Okay.
You look at, yeah, when it's the first part of the language, yeah. You should, wouldn't you think?
Yeah, I would think so.
I'm just waiting for Rob to walk back in, because then I
Okay.
know that people are back from coffee. Seems to be quite a big, good stream now.
Sort of repetitive talk, sort of discussions going on.
Yeah, but I do think we should start soon, because otherwise.
I think so, yeah, or else
So
we'll
it-
lose more people who are going to the train.
Exactly, so I'll wait like the last 30 seconds or something, and then
Yeah.
we'll just start anyway.
Perfect.
Yeah? Don't want you to miss that very expensive train now.
Yeah, no, exactly. I forgot to buy my tickets. I'm flying from Brussels to Munich because I have a friend that I'm gonna visit in Brussels, but I forgot to buy a ticket for the Eurostar, and by now it's 300 euro.
Yeah, I know, it goes up at the last
Yeah.
minute. I discovered
And then now
that.
it's also it's first class, so now I'm gonna be very
Oh,
comfortable because the second class was.
Okay, so welcome back for this very last highlight session of the conference. And unlike the written in the program, we swapped the last two talks. So instead, you will now have Lucas giving us his impressions from the particle physics side of things.
Yeah.
Go ahead.
Thanks a lot. Also, thanks to Luisa for swapping with me because I need to catch a train. So we have these impressions. So I also understood that it's customary here to declare whether or not you're Bayesian or frequentist. I will say I just play both sides. So if I write cosmology papers that are frequentist and particle physics papers that are Bayesian. So I just try to rile up both communities. Okay. So I was very impressed by Kyle's 5-dimensional outline. So I upped the ante, and so I have a 14-dimensional outline. I swear there's some structure to the talk, but it will be very difficult to understand. So Jeff Hinton, he's one of the kind of godfathers of deep learning. And so he said, okay, to deal with 14-dimensional space, you visualize the 3 space and say 14 very loudly. So this is how to think about the outline of the talk. Okay, so then we had those discussions with Louis on, okay, do we have enough statistics at this PHYSTAT, or is it too much machine learning? And so there's also sometimes this discussion going on, like is machine learning just applied statistics, or what's going on? And so I wanted to spend a little bit of time just discussing, okay, where can statistics maybe help in understanding machine learning. So there's also this kind of nice exchange where David Pfau, who's a machine learning researcher, says, okay, whenever people say statistics and machine learning are the same thing, we should recognize that none of the machine learning people don't know anything about like hypothesis testing and all this stuff at all. And of course, except logistic regression, which is on the lower right-hand corner. And but why are we interested in machine learning and statistics? And so in high energy physics, these things come together. And I just wanted to kind of re-stress that so somehow machine learning, high energy physics, and other sciences are super deeply related, because it's exactly this likelihood-free setup. It's exactly the same thing in both of these fields. So we have kind of like a high-level concept that was not accessible to us, so the labels. We have a stochastic generator that produces samples. So either these are samples that we collect in real life, in the case of machine learning, or samples that we can produce with the simulator. And so we have like these two sides where we have like the generative process, which is likelihood free and produces just samples. And then what we want to do with these samples is to do inference, and we want to get back from the low level data to the high level concept. So for us, this is kind of measuring things like some aspects of the Lagrangian or something like this. And then in machine learning, it's exactly the same thing. So you have some high level concept. For example, language has been very kind of en vogue in the last few years. And then you can generate images. So this is generative machine learning. And then kind of more discriminative machine learning as you go from the low level data and you try to recover the high level concept. So it's a very close parallel that I think explains why, I mean, particle physics has always been using machine learning, or back in the day, multivariate techniques for a long time. And so now machine learning took off in the last 10 or 15 years. And so I think one thing that Tillman also stressed, and Raman as well, is so there's been a lot of focus because things were moving so quickly to just kind of get ahead of the technology and just learn the tool, right? And so there's a lot of kind of iterations where people weren't maybe necessarily sure like what something is useful for, but it was just about learning like these types of like a technical capability to learn what Tillman called as new numerical tool. And so I would say we've gotten very good at this. So this was kind of like the cowboy phase of machine learning and particle physics. And so people just track the literature in in machine learning. And so now we are very good. Okay, some new architecture comes out, and so within like a few weeks, there's probably some high energy physics paper that uses the architecture. So for some new generative model comes out, and right away we have some kind of paper. So we've become efficient at understanding and using the technology. So I think that's great. And so I think it's actually very good because, so I'll make this point in a bit, but so then the question is, okay, is it only about technical capability, or what do we want machine learning to do? And so Raman had this nice German expression that I also like, the eierlegende Wollmilchsau. So this is basically someone saying, okay, you want everything. So you want to like have the pie and eat it too, right? And so you want like some machine learning magic that does something that you would maybe like to have, and it's unclear whether or not machine learning can actually provide this thing. And I think this is basically where statistics can play a role. But it's not to say that this type of Wild West phase is not useful. I think it's extremely useful because in a way, machine learning is so successful in the last 10 or 15 years because basically there was like a ad hoc, refutation of theory. So, I mean, a lot of this connectionist machine learning for a long time was second to kind of more theoretically grounded approaches. And so by kind of ignoring all of this theory and just barreling ahead and just trying stuff out, I think this is how a lot of progress in machine learning is done. And so this type of, just try things and see where you get empirically is very useful. But I think once we kind of get control over this technology, I think it's useful that statistics can in some way help tame ourselves or kind of figure out, okay, what can it actually do? Or, are there some kind of impossibility results that Mikael was also mentioning? And so sometimes you also discover, some things in machine learning or rediscover some things in machine learning that seem new, but then actually turn out to be very old statistics. So one of the examples was this double descent. So this is this normal bias variance trade-off. The first half of this plot is the bias variance trade-off. This is basically this statement that, okay, as you increase the number of parameters, I mean, you can, fit anything as precisely as you want, but then your generalization becomes bad. And so then what people realize, and so this is what Pierre was saying, is once you go to hyper over parameterized models, then the generalization properties become better as well. And so this was in a way kind of first sold as a type of, machine learning magic or something like this, the magic of double descent. But then later they realized that this is actually something that you can reproduce with like splines in a single dimension and so on. And so it's actually kind of some old statistic. And so this reminded me a little bit about kind of Feldman cousins and the high energy physics, where, okay, the physicists in this case, developed something ingenious and then later on figured out that this was something that was already well known in the statistics literature. And so now where can statistics kind of play a role? And I think there are multiple ways to think about it. So we can basically do this game kind of like double descent or like, statistical learning theory, that we use statistics to create kind of the foundations of machine learning, the language, probabilities, kind of like some kind of theory around machine learning and so on. And so in a way, this is like this view that machine learning is kind of applied statistics. And at the core, somehow around statistical learning theory, I think that's still true. So the other direction is kind of this SBI direction, where we use machine learning basically to implement the statistics workflow that we want to do, right? And so the normal statistics workflow, we would know how to do it, but it's too slow. And so we just use machine learning to accelerate it. And so I think that direction also exists. And so then how does this relate to physics? And so physics, basically, we can kind of draw from both fields. And so say, okay, from statistics, we learn, okay, what do you need to do like a good statistical inference? You need like a good summary statistic, right? So this is what normal statistics tells us. And then we can turn to machine learning and say, okay, if I need a summary statistic that is somehow very efficient and kind of capturing the information sufficiently or something like this, we can go to machine learning and maybe it will provide us the summary statistic. And then finally, so this is maybe like the original kind of interest of PHYSTAT, is that, so with PHYSTAT is we were always asking ourselves, or maybe flattering ourselves, that could we as physicists provide something to statistics, right? So, and I think the original PHYSTAT view is maybe actually some of the stuff that we're doing at frontier physics experiments, like thinking deeply about how to do like limit setting in various kind of extreme cases, actually turns out to be like research level problems in statistics. And I think that's bore out, which you can see by like the attendance of research statisticians at PHYSTAT. And so now you can ask yourself whether or not the same direction also holds for kind of for physics to machine learning. And Max had this point of view in his slides, and whether or not machine learning needs gravitational waves. And so you can extend this to, okay, does machine learning benefit from physics? And so I think it's true what Max was saying, that the rigor in science, like the level of accuracy that we need in kind of these types of high stakes science experiments, really stress tests some of the machine learning applications. And so we see this by the time that it takes to implement them and put them into production, that it's not obvious. So it's not like machine learning swoops in and so solves all of our problems. Okay. And so then some of the things, so I just wanted to highlight some of the things where like a statistical point of view is useful. And so the one is like anomaly detection. And so I think here's like, and it's not like necessarily machine learning, but statistics can give us a lot of clarity of what's possible and what's maybe not so possible. So Lily had this great talk about anomaly detection, basically saying that kind of like in general, like some kind of eierlegende Wollmilchsau, so some anomaly detection algorithm that somehow has power everywhere is not possible, right? So you need to specify something about the out of distribution. And so ultimately this goes back to basically the statement that there's no universal most powerful test other than in a kind of 2-point hypothesis space where it's going to be the likelihood ratio for the Neyman-Pearson lemma, right? And so we need to somehow specify. And so I think the point that we are struggling with as physicists is how do we do the specification, right? And so kind of specifying this out of distribution, where we want to place power is, I think, the key in anomaly detection.
And so the question that we need to ask ourselves, okay, in what language do we specify? So we are kind of hesitant to specify it at the level of like a Lagrangian, right? Because that's exactly what we don't want to do. We want to somehow have like some kind of model as agnostic as possible point of view. But then what is the language in which we can formulate these alternatives, if not kind of at the level of a Lagrangian, right? And so I think this is ultimately a challenge to the theorists, is basically they should think about how can we specify theories or equivalence classes of theories, that we can somehow reasonably say we care about without kind of enumerating these are the particles, these are the couplings, and so on. And so we already made one of these steps. So we went from kind of these, UV complete theories, grand unified theories to what we now call simplified models. So in a way, it's already like an abstraction where you kind of remove a lot of kind of the actual physics, and you really somehow just have like kind of straw man versions of theories. And so, but this is still something like, I think the anomaly detection push is something that we're also still uncomfortable with. That's still too much model specific to us, right? So a simplified model might still be like some kind of supersymmetry model. And so then what's the next step? So is there like some kind of other language in which we can specify theories, that is more abstract, but still captures like the physics sense, that we're not interested in some random detector noise, but we're interested in some, high PT new physics, right? And so Gaia had like one take on this where it was, okay, so maybe you can somehow parameterize a likelihood ratio in some way. And so the question is, okay, to what type of physics does this map to? And so this is something I don't really have a good answer for. And so I think this is also what's kind of, why bump hunts, which is more or less the only anomaly detection setup that really kind of made it into production at the LHC, are working, because bump hunts do exactly this. So they somehow specify like an equivalence class of theories or some type of theoretical setup without kind of overly specifying any physics, right? So you're basically saying, when you're saying I'm doing a bump hunt, you're saying I don't care what the couplings are or what the spins of these particles are or whatever. I just say there's going to be some kind of resonance. And so I think kind of the holy grail is, okay, what's like the next type of bump hunt? So is there some kind of language where we can go beyond the bump hunt, but stay at the same kind of vagueness of model specificity? And so I don't know. So this is I think something that the theorists have to tell us whether or not such a language exists. Okay, so then there's like, I think Thea made this point very nicely. And so anomaly detection, I think kind of works best if it's really coupled with reinterpretation, because I think it really captures what we're trying to do with anomaly detection. You're trying to not overly focus on like a specific narrow set of theories. And so, okay, we realized from Lily's talk that, okay, you can't have power everywhere, but you can still like make a choice where you want to have power. And you can say, okay, instead of over optimizing on a specific theory, I can choose to place some power, around this theory space, however we, kind of in whatever language we parameterize it. And so, yes, you're basically giving up power for like any specific theory, but what you gain is like some reduced level, but non-zero power for lots of other theories. And so now you can test with the same analysis a lot of theories, and while you might not be optimal, you might still be able to somehow constrain like a larger set of theory space. And so I think coupled with reinterpretation, this type of kind of vague event selection that you might get with anomaly detection makes a lot of sense. Okay, so I will say that actually, so this is also what Mikael was saying, is like in a way like the original frequentist derivation on why we're using the test statistics we're using follow exactly this type of argument. So the reason why we use the profile likelihood is not because it has like maximum power with respect to like a single alternative, but because it has like optimal average power for some set of equivalence class of theories. And so now Mikael basically said, okay, instead of saying, okay, I want to have like uniform power for alternatives that are somehow equally far away from the null, what you can do, you can even like introduce some kind of weighting function. So it's kind of like a frequentist prior in a way, where you really kind of
explore, okay, where do I actually want to place power and where not. It doesn't need to be uniform in any kind of metric. You can actually play with this and really kind of start to do physics in this way by kind of declaring what your preferences are in theory space. Okay, so then yeah, so I think I think this is a question that I asked to Thea also after her talk. Is to me as an experimentalist, I think a useful framing, and this is a question I ask very often in anomaly detection talk, is okay, so let's say you have like 5 groups in an experiment like Atlas that come up with 5 different anomaly detection algorithms, but you can only deploy one because this is how much space you have in the trigger. And so what is the decision-making mechanism that you used in order to choose which one of the 5 to deploy actually in your trigger? You can only, so you have 5 options, you can only deploy one. And so very often, basically, somehow this does come down to like some kind of preference that you use, like, okay, how does this anomaly detection algorithm work on some kind of benchmark models? And so there implicitly, you're basically making a choice in theory space. And so once you make this choice, I think, so, there was like a big jump in technical readiness. So from Thea's talk, where we know that, okay, once we are kind of clear how we would make this choice, we can absolutely implement these types of kind of more advanced event selection mechanisms at a very core level inside of the data acquisition system of the LHD. So like the trigger. Okay, so then I wanted to, so maybe statistics can also give us a little bit of clarity on generative models. So basically it's the same. So I'm happy that we were kind of converging maybe on the summary. So there's some convergence between the summaries maybe. And so I wanted to basically repeat the argument that Mikael was also making. So, okay, there's like this question or the prompt that Louis had, okay, can you really create information out of nothing? And so I think, like, unsurprisingly, the answer is no, right? And so, but how do we understand what's going on? And so I think kind of to me, it's useful to think about like this as a density estimation. So now you can imagine you have some kind of density, and now you can sample from this density, like giant or something like this. You can imagine this black density is giant. And so you're sampling some low number of events out of this. And so now you do like a histogram. A histogram is a density estimation technique. And so what does this histogram look like? It looks something like this, right? Okay. And so you might draw some other event, right? And so depending on which events you draw, you get like a different histogram. And all of these histograms in the space of densities, they sit somewhere, right? So kind of each one of these samples gives you like a estimate of a density. And so in the space of density, you're kind of with a fairly high variance populating this space of densities. And so now we can think of this, okay, what is this procedure of sampling from a density plus histogramming with as a density estimation technique? What does this estimator, what kind of properties does this estimator have? And in a way, it's an unbiased estimator because we're sampling from the true distribution that we want to approximate, right? So it's going to be unbiased in a way, but it's going to be very high variance, right? So because every time you do like, so histogramming doesn't have any regularization techniques. And so it's a very high variance estimator in a way, but it's unbiased because you're sampling from the real thing. And so this is usually what we call like the MC stat error. And so now the flip side is basically what Mikael was saying, okay, like nobody is forcing us to do histograms, right? So there are a bunch of different density estimation techniques. We could just do like a kernel density estimate. So we place a kernel on each one of these kind of little data points, and then we have like a kernel density estimate. And so now, of course, this is a different density estimate. It's also a density estimate. And so this density estimate also lives in the space of densities somewhere, right? And so maybe it lives closer to like the true density because regularization assumptions or the implicit bias that we have in this, maybe in the choice of the bandwidth of the KDE, somehow matches the properties of like the true giant distribution. And so now we can say, okay, what as an estimator, so now, okay, it's KDE, but you can basically call it a fast simulation because you can sample from it, right? You can sample from a KDE. And you can even, it's a density estimate, it's like a kind of prehistoric normalizing flow. You can also evaluate kind of the density itself. And so now you can kind of think of this, so what are the properties of this KDE? And so if you sample like some large number of, or like some small number of samples now from the KDE and you histogram again, then, okay, you still get some kind of high variance. But because the KDE is fast, we can sample like an infinite number of samples very, very quickly. And so basically what we get with this KDE is like the flip side of the estimator. It's like a biased estimator because, of course, with limited amount of information, you cannot get to the real distribution. It's impossible. There's a finite amount of information. So it's going to be biased, and this depends basically on the choice of your hyperparameters and the training data. So every time you use a different training data for your generative model, you'll somehow land somewhere else in this density estimation space. But it's going to be zero variance because sampling is either you have like a tractable density, it's like a normalizing flow or a KDE, or you like sampling is so cheap that you can basically sample an infinite number of samples and histogram that, and that's basically going to be zero variance, right? And so to me, basically this is kind of like a bias variance trade-off. And so just to see what is happening is that, okay, you know, with sampling GEANT, what happens is as you're sampling more and more events, you'll get closer and closer to the true distribution, right? So you kind of can reduce the bias or like the mean square error to like in this density estimation technique, you know, to zero, like as much as you want. But sampling from the generative model or any type of KDE that is trained on like a limited set of training events will never reach there. So there's like this non-zero bias, and so you kind of you know, flatten out, and you will never reach the true distribution. And so where's the benefit? So when people say amplification, what is going on? And so basically what's going on is, so here the x-axis is the number of drawn samples, and but now the every sample from the generative model is very much faster. So actually that timeline gets compressed, right? And so you kind of can reach this plateau much more quickly, or even if you have like a you know, like a density model, like a normalizing flow, you don't need any samples at all, right? And so now you see like this amplification business where you're basically saying, okay, if this is like the accuracy level that you're targeting, basically you can either you know, draw like 1 billion events from your generative model and basically just you know, sit here, or you draw like some kind of large number of GEANT. And so the fact that you're kind of using less resources here, you know, this is basically what is this amplification business. And to me, it's some version of this bias variance trade-off where you're trading off like a zero bias, high variance strategy where you're sampling actually from the expensive simulator versus a biased but zero variance strategy, which is basically, you know, like a KDE or a flow or a GAN that is so cheap that you can, you know, very easily sample like 1 billion events out of this. Right, and so like the game is, okay, can you reach like an MSE in a shorter time? So I will say it's a little bit of kind of like an apples to oranges comparison, because what is happening is that you're comparing like using few samples, but a very fancy density estimation technique. So, okay, you have like a few samples from GEANT4, but then you use like some generative AI thing, and you're comparing it to many samples from GEANT4, but you decide to not use any fancy density estimation technique. You just say, I'm going to use histograms, right? And so now, okay, if you kind of have this asymmetric setup, you can be in a situation where you kind of win with the kind of left-hand side over the right-hand side, but you'll never win kind of with fewer samples and fancy density estimation against many more samples and density estimation, right? So the KDE on like 1 million events is going to be stronger than the KDE on 10 events. And so I think this amplification basically comes out of this asymmetry. And I will also say that this is a one-time gain, right? So this is, you cannot kind of, there's no general rule where you can say, okay, maybe like every event that I get out of my generative AI is worth like 100th of a GEANT4 event. Because at some point, like every additional event, there's like diminishing returns. And it just, you know, at some point you just saturate the thing and you just don't learn anything anymore. And so you will never kind of be able to reduce this error to zero. And so, yeah, so you can gain once kind of through this regularization, but then you cannot gain anymore. Okay, so I'll see how I am with time. Okay, so this was, so I was happy that Mikael already touched on this, but I thought because it was one of the prompts I would, and we never really discussed this, so I thought I would discuss it a little bit. Okay, so then interpretability and control was a big topic. So
okay, it's not only that we want to tame us in terms of how we use machine learning, but maybe we also want to tame the machine learner, or really understand, what's happening. And so, the core question is, what are they learning, right? And so in a way, Jesse had this nice discussion on, okay, do we want it to be interpretable and so on? And so I think he made a very good point that it's basically our desire to be interpretable is a desire to retain control over the process, or somehow retain control in an uncertain world where some things might not actually correspond to the assumptions that we have. And, we might not fully trust the process, right? And so this type of iterative behavior, or some kind of hope for introspection is not new. So in Bayesian statistics, so there was like this trend towards like what they call Bayesian workflow. It's kind of like some iterative model building where you fit multiple times. So if you would completely trust the process of Bayesian statistics, you would just write down your likelihood, you put in your prior, you run your MCMC, and without thinking, you just get your posterior and you're done, right? And so people kind of realize that it's better to somehow be able to introspect the system and play with the system, maybe develop the model in kind of like some kind of iterative way. And so like in a way, kind of this is also somehow like a desire to understand the process, or, because you're not trusting the models. And George Box has this famous quote that you're not trusting the models because all models are wrong, but some are useful. And so I think that basically this interpretability desire comes from the same direction. And so, yeah, Jesse had this thing with the likelihood ratio. So when you trust the process in the sense that you trust that the simulator is correct, there's nothing else to do than just to train like a, like a likelihood ratio estimator, like with binary classification, then you're done, right? There's no reason, as Jesse is saying, to somehow expect that this should have some kind of nice functional form. And, if you completely trust the setup, usually we are fine without interpretability. We care about interpretability when we somehow suspect that something might be wrong with our setup, so that we want to kind of retain our ability to go back and try to really understand at some lower level of detail what's going on, right? And so one example is kind of this performance under intervention. And so this was also, Mikael, so there's a hyperconvergence. So I do think so, like, so the type of things where we are kind of unsure in particle physics, we don't trust our simulators. We think our simulators are great, but, we also know that they're limited in some ways, and Bob Cousins also make the same point. And so like Sherpa versus Herwig is like two different ways to do quantum chromodynamics, so this corresponds, like changing one of these things in the simulator would correspond to like an intervention. You're changing the joint distribution. And so what we're worried about is that the neural network or the machine learning system will learn something that really depends crucially on this choice, and we don't want it to depend on this choice. And so there's a lot of literature on how to kind of explore things where you can do interventions. And so in the real world, we can't do interventions. So in that sense, we don't have any causal inference problems, I would say. But at the same time, we very much can do interventions in the simulator because we have it available to us, and we do actually do them all the time. And so the way that we do two-point systematics, I think, is basically an intervention, but we never kind of phrase it in the language of causal inference. And so I agree with Mikael that so this is actually maybe something that should be revisited. Okay, so then so part of this kind of interpretability or control or retaining control is, I think, inductive bias. And so, of course, as physicists, we're very, keen on using our domain knowledge to help the dumb machine. And so I think there are basically two ways to think about inductive bias. So there's like a kind of, like in physics, where you have like electrostatics and electrodynamics. I think there's like a statics and the dynamics version of inductive bias. So the statics version is what we usually think about inductive bias as somehow enforcing symmetries or guarantees in a neural network. And so this works well. And then I think there's like a separate point of view, kind of the more dynamic view of inductive bias, where we don't want to give up control for everything and hand it over to the machine learning, but we want to use machine learning in like a controlled way, kind of in like a walled garden where we know what's going on, and we embed it in like a larger machine learning workflow. And so, okay, so this was one example. So, okay, we have, geometric algebra, spinors, and all of this stuff. And so
I think this is great that we are able to kind of introduce this inductive bias. I think one worry is a little bit that the symmetries that we care about, they hold in the latent space. So nothing at the level of experimental observations is actually symmetric. And so it's not clear. So we kind of have like these softly broken symmetries, I think, in the observed data. But nonetheless, I think that this is great and it helps a lot as we see from the results. And so the soft symmetries, I think, was mentioned by Kyle, where you want to force some behavior on the machine learning system so that you want to kind of enforce some kind of approximate invariance and so on. And so this is somehow our desire to have control over the machine learning system so that we control how it behaves instead of the machine behaves in some random way that we don't know. Okay, so the other more dynamic version, I think, is a little bit kind of like, this SBI versus matrix element story. And so here, basically, we have two ways to do kind of optimal inference, or optimal observable. So you can either do SBI, right, or you can do matrix element method. And so they basically do the same thing. For matrix element methods, so you kind of estimate the density, like P of X given theta. But you don't estimate it in like a zero shot, like so the neural network just gives you P of X given theta. You split it up into multiple pieces that you maybe attack with machine learning, but then you put it back together on our own with the physics knowledge that we have, right? And so like the data flow is something that we control, and we give like small little tasks to the machine, but then we kind of tie it back together as physicists. Whereas SBI is kind of like the opposite, where it's like, okay, I don't care, like you SBI go and you just estimate the likelihood ratio. And so I think this is basically like this story about kind of retaining control that, I mean, like the left-hand side, the matrix element method, much easier to debug because you can individually test like the transfer functions, you can test the sampling, like the integration, you can test like the efficiency and so on. Whereas in the kind of SBI, the diagnostics are not so kind of physically accessible. And so now you can ask yourself, should you ever do matrix element method after we realized we could do SBI? And so in a way, yes, like if you want to have this fuzzy feeling and this debuggability, so that's great. But I mean, we should realize that this fuzzy feeling comes at a very, very steep price, that we need to do this integral. And so there's a reason why, a lot of matrix element methods kind of, is very, very slow. And so we need to somehow decide how much do we care about this interpretability and how much can we leave to the machine learning. How am I doing with time? Like 5 minutes? Perfect. Okay, and so then the extreme version of this kind of more dynamical point of view of inductive bias is what Arthur showed, is that basically you have like this data flow that is like some kind of mixture between physics and some pieces are machine learning, but you still treat this basically as a big neural network that is somehow has like some kind of funky physics specific architecture, and you just still end-to-end optimize this with differentiable programming and back propagation. And so he showed that there's basically like a two-step procedure where you first kind of train like a physics unaware neural network, and this is your starting point. And then you fine tune with the physics knowledge kind of as a second step. And so in a way, this is similar to what people do nowadays with foundation model, where it's kind of pre-trained as an initial kind of, representation of the analysis, but then we fine tune to kind of get the optimal analysis out. Okay, so then I think my overall kind of take on interpretability is a little bit when I studied physics, I was kind of confused. I learned like special relativity and quantum mechanics, and in a way, it's not very complicated, right? So quantum mechanics is a little bit, some linear algebra, special relativity as well. And so I think if you grow up with special relativity and quantum mechanics, it doesn't seem so mysterious, but it was very mysterious to the people that discovered it. And so I think in the way it's like intuitive and interpretable is basically what you're used to. Right, and so Tobias also made this point that nobody thinks about the flavor tagging algorithm, like trying to interpret how it works. We just find that this is just like some kind of black box neural network, and nobody really thinks about it because we use it as a type of, some kind of instrument that we can calibrate, and then, we don't care how it works internally because we know how to calibrate it. And so I think kind of as time progresses, we're going to be more and more comfortable with bigger and bigger tasks being done by machine learning because we just get used to these tasks being not as interpretable as we think. Okay, so I'll not spend a lot of time on simulation-based inference because Gilles gave a very nice introduction. So I will just say, like, the way that I mentally structure this thing is that I kind of see 3 generations of statistics. So there's like the version 0 statistics, which is the pen and paper statistic, the stuff that you can do without a computer, right? And so both Bayes and frequentists have kind of this quality where, like, in Bayesian statistics, it's, you know, like conjugate priors and Kalman filters and so on. You can basically, do everything. You can produce a posterior by hand, right? Because, but I mean, you're somehow using some very strong assumptions that you might not know that don't hold, but you kind of make this compromise because in favor of having it computable, right? And then the frequentist sense both this also exists. So this is this, like, the area of distribution-free tests and asymptotics and so on, where, I mean, it doesn't matter what my model is, it's going to be chi-square distributed, and you somehow, maybe you don't really trust this assumption that you're going to be in an asymptotic regime, but you kind of suspend disbelief, because it's going to be make your life easy. And so this was like version 0. And I think then version 1 is kind of this more kind of computationally heavy version where we actually have the computing power to do it. So this shouldn't be pen and paper statistics, should be a different name. And so this is where we actually do like some detailed modeling. We have like a very principled workflow. We, figured out MCMC, or we can use the computation power we have to actually empirically estimate the test statistic, sampling distribution. And so this requires a computer, but it's very principled. And so then you don't need to do this compromises of assumption that you maybe don't trust. And so, but you're still somehow creating the model as a type of graphical model. And so then the version 3 of statistics is somehow like this area of implicit models where the graphical model, you don't write it down anymore, but you basically have it as computer code, and the model is defined implicitly as software. And so then we use machine learning to provide us with fast, approximate, amortized inference. Okay, so Gilles had a much better summary of the SBI stuff, but so I think I had the same interesting insight, or I didn't know before that somehow, like in gravitational wave, I didn't appreciate before that they actually had the likelihood. And so that this idea that you can use SBI mostly for the amortization properties and kind of the quick inference, and not necessarily because you are in a likelihood-free setup, I think is very useful. And so then there's like a little bit of a bridge between this version 2 and version 3 of statistics, which is differentiable and probabilistic programming, which I didn't have time to digest in detail, but I noticed today a lot of people mentioned differentiable simulators and probabilistic simulators, and the fact that they speed things up a lot. And so it's also something that we tried to do in particle physics a few years back. And so I think this is a very exciting setup where somehow we're improving the computer, like the programming languages that we have. Okay, so in high-energy physics, I would say, so SBI took off in Astro much more quickly than in high-energy physics, but Ishik, I think, convinced me that, okay, maybe it's not so too distant future, we'll have a step change where you go from 0 SBI analysis in high-energy physics to 1 SBI analysis in high-energy physics. And the thing that I worry about is how do we make sure that 1 to n then is not as difficult as 0 to 1. Okay, so I'll maybe skip this. Okay, so it's only 2 more slides. And so then I think from a statistics point of view, basically what SBI does is it replaces some part of the statistics pipeline with machine learning, right? And so now the question is also in terms of interpretability, how much statistics do we let the machine do, and how much do we want to do on our own? And so this is also something that Kyle mentioned. And so, like, for example, neural posterior estimation is basically single shot, like the machine does everything. You put in the data, the machine gives you the posterior, and you're done. And so Max had like a interesting version where then you do like some kind of importance sampling as a second step, or you can do like more neural likelihood estimation, then you run some MCMC. And so then it's some kind of mixture between like machine learning based statistics and actual traditional statistics. And so we have the same thing in frequentist, in the frequentist setup, where either we use the machine to learn the neural likelihood ratio, and then we do the profiling in the traditional way, or we directly learn to profile. And so here, I think it goes back to the same question, like how much do we trust the process? Do we really trust the machine to do all the complicated profiling, or is this something that we want to do on our own? And so then, okay, the last slide is, I will not spend a lot of time here, is basically, okay, so this is simulation-based inference, and a lot of people don't like the simulator, at least the detector simulator. And so I think this is where you get into this unfolding. And I think, to me, this is basically a reminder that it doesn't matter what the technical setup is. It's really like high-energy physics has always been like a social enterprise, and some of the core questions a little bit, okay, what's the most useful setup for like long-term exploitation of the data that we collect at the LHC? And so maybe it's folding, or maybe it's unfolding, and I think the both sides of the story still improve. Okay, with this, I'll do my summary. So I think we're very good at learning new machine learning methods. I think classic statistics still has a lot to say about kind of guiding towards telling us what's possible and not possible in terms of like impossibility results and so on. I think interpretability is a lot about trusting the process, and domain knowledge still helps us until maybe at some point it doesn't, and then we hit this bitter lesson. Okay, thanks.
We have time for a few questions. If there are. We can have another discussion about whether or not interpretability and what it means. I asked a question about your interpretability. Yes. Because you mentioned about trusting the process, but in the end, it's been mentioned in previous summaries as well. I mean, it's not just about trusting the process, it's also trusting that we know which question we want to answer.
Right.
Right? You would agree with that?
Yeah.
Okay.
Yeah.
Okay.
No, yeah. So I mean, if the question you want to answer is, I want to kind of estimate the likelihood ratio as best as possible, then like, nothing is maybe better than training the classifier. If you want to somehow convince yourself that you understand every step of the way, then you need something more interpretable. So yeah, so I think what Jesse was saying is that, interpretability comes in when we maybe don't feel like we really specified the question correctly. I think this is close to what I feel as well. Yeah.
Any more questions?
No, that's fine.
If not, then thank Lucas again. And we have the next talk, which is the So I have some signs. I'll hold them up for 5 minutes. Okay. And 1 minute. There's no pointer. No, so because of people online, we can use the mouse.
Okay, so can we hide this? It's already, okay.
Yes, and you use the arrows to switch slides.
This one.
Yeah, as long as you stay sort of in this area, the microphone will pick you up.
Okay, now we'll try. All right. Okay, hi everyone. Last talk of the conference. Hope you still have some energy. I'm Louisa Lucy Smith, and I'm a fellow at the Max Planck Institute for Astrophysics in Munich. And yes, I'll be telling you a bit about some astrocosmo highlights from this conference. So let me just start with saying that in cosmology, our goal is really to try to connect our theories to the observational data that we have. And as many people said throughout this conference, we're really not data limited in cosmology. We have lots of ongoing and upcoming data from, spanning the universe at very early times all the way to today, and on very different scales. And so the kind of cosmological models that we're trying to build are kind of built on, solid theoretical frameworks such as general relativity and the standard model of particle physics, and then have, these less theoretically motivated elements like inflation telling us about how the universe started, dark energy and dark matter. And so it's really trying to understand this fundamental physics that is still motivating us to do this theory versus data process. And so what are the challenges in trying to connect our cosmological theories to data? And so we have a bunch of, at least on the theoretical computational side, first of all, we're mostly dealing with very computationally expensive cosmological simulations that try to cover as much volume as possible and as much high resolution as we can to really model the physics of galaxies. And this process is very highly nonlinear. And so again, we need these computation expensive simulations. We also, we don't have the ability to just run these simulations and know everything that we're putting in because we have uncertainties in the actual galaxy formation process. And this then leads us to, high dimensional and intractable likelihoods, which also makes these typical likelihood analysis difficult to solve. And then ultimately, what is the connection between these cosmological models that we build to that fundamental physics? And at least in my view, just fitting cosmological parameters doesn't really mean understanding. And I'll go back to this, also mentioning interpretability. Okay, so I think in this conference, we've heard many successful applications of AI that in different ways try to solve these theoretical challenges that we have. And I try to split them into these kind of 3 threads. One in terms of, building models to try and accelerate these computationally expensive models that we have to deal with. Then, trying to go to this new kind of parameter inference paradigm of implicit likelihood inference or simulation-based inference, where instead of writing down an explicit likelihood, you try to learn it by basically having a forward model that gives you the data and then trying to learn the joint probability distribution of your data and your parameters. And then I'll touch also on explainable AI. That is, one of the, I think, opportunities in using machine learning in cosmology to try to actually, come up with some scientific discoveries that are machine learning driven. And I just wanted to make the point that I think here at this workshop, we're predominantly in a bubble of machine learning enthusiasts, but I think in the astrophysics community, this is not really the case, right? There are a lot of still machine learning skeptics. And so I want to give a slightly broader overview of how the astrophysics community sees these kinds of results and how we can try to bridge this kind of 2 different groups of people, those that are happy to use machine learning, even a bit too much, right? Using machine learning blindly, even when maybe you don't need it. And those that just, refuse to acknowledge any new finding from machine learning results. Okay, so let me start off with the generative models, sort of emulating forward models highlights. So the first thing, that I think in cosmology we're pretty good at, and people, have started to use these models even in more traditional analysis in big collaborations, is basically emulators for summary statistics. So these are summary statistics that we use to approximate the information that we have in our fields, either in the CMB or in large-scale structure, that we can directly compare to observational data. So I just want to highlight here CosmoPower. It's a suite of large-scale structure and CMB emulators by Alessio Spurimancini. I don't know if he's here, but there are really many emulators that have been developed in the field, such as, for example, the Baco emulator for the linear matter power spectrum, the nonlinear matter power spectrum, and from the Emulus group for something like the halo mass function, so counting the number of halos as a function of their mass. And so these are now, emulators that are being used to really speed up the computation of these summary statistics that can then be used compared to the data. So people have then, taken this one step forward and saying, okay, we don't just want to emulate the summary statistics, but we can actually try to emulate the full field. So this is, for example, an example of what I think is the state of the art in these field level emulators, and it's work led by Drew Jameson, where essentially you take as input, a cheap linear field, so the displacement field, and then you try to emulate what the results, the fully nonlinear displacement field that you would get from a simulation. And this is done with VNets and with style parameters that include either cosmological parameters, so you can produce these outputs as a function of cosmology or as a function of time as well. And typically these emulators are then validated or tested against, again, summary statistics. And you can see here kind of in pink that for the power spectrum or the bispectrum, these emulators work really well compared to the n-body, the ground truth or the n-body simulation. And we've also seen in work by Matt Price that was presented in one of the posters that there's also these generative models that you can do on the sphere. So going, one step closer to the way we actually observe the data. Again, for large-scale structure fields or for TSZ is another probe that we use in cosmology. And these are done using scattering transforms. There are new summary statistics that is known to also capture nonlinear information from the fields very well. And so again, it generates fields that very much look closely to the target or to the ground truth that they were trained on. Okay, so emulators are great, and we can apply them to field level, so to actually create what you would have with the cosmological simulations, but they still have some errors. And it turns out that the errors of our field level emulators are larger in the places where we really care the most about, where things are most nonlinear. So for example, at the center of dark matter halos where galaxies form. And so Deglan Bartlett, who also presented a poster here, showed that actually it's possible to use machine learning as a big step towards to try to get as close as possible to the target, and then use our typical gravity solvers to try to correct for those emulator errors. And so this is called COCA. And what you see here is essentially this reference would be basically the output of the emulator, so as close as possible that you could get with the machine learning part to the target. And then with just 24 evaluations, you basically get to negligible residuals with respect to the actual M-body. And so I really like this framework because it combines, perturbation theory, which does the first simple step, machine learning that does a big chunk of the nonlinearities that are very expensive, and then we apply our physics knowledge, the last force calculation, just to correct the machine learning errors. And so this in principle can give us very precise and very good predictions for an equivalent, an M-body surrogate model, essentially. Okay, so the next sort of topic that I wanted to highlight is in the field of simulation-based inference. And as we heard from the other speakers and the particle physics, I think, in cosmology, we're really at the stage where we've done the proof of principle part, we've done the validation on mock data set, and we're really at the stage where we can apply these kinds of inference pipelines to real data, and on the same par as the traditional likelihood analysis that are being employed in the collaborations. So this is one example of such an analysis that was presented also in one of the posters by Kiam Lin. So this is basically a simulation-based inference work for a weak lensing 2-point summary statistic. And so the key thing here is to have these realistic forward models that can produce this 2-point summary statistic that we use, that includes all the systematic uncertainties and all the survey specifications. And then the pipeline basically consists in taking the simulated data, compressing it. In cosmology, most of the time, we don't do density estimation on the full simulated data, but in a compressed version of it. And then we learn the likelihood from this simulated data as a function of the parameters. And I like this work in particular because it actually showed that when you used simulation-based inference compared to a likelihood analysis, so for example, it's a bit busy, but if you compare the orange to the black, you see that actually SBI has broadened the errors of these contours. And this may suggest that, for example, in our likelihood analysis, we were making choices, more restrictive choices, that what you can put in your forward models in such a way that we're underestimating your errors. So another example of this simulation-based inference, fully application to data is work by Niall Jeffrey that gave the intro talk on Monday. And this time, not even just using, a 2-point summary statistic, but using an actual map level. So in principle, the full information that you have in this case, also for weak lensing. And again, the pipeline first compresses this information from the field into a a lower dimensional compressed summary statistic with a convolution neural network, and then does the simulation-based inference step. And in this case, because we're using the entire field and not just, you know, a 2-point summary statistic, you can see that they find in blue, if you compare the blue to the gray, they find much tighter constraints compared to the traditional 2-point likelihood analysis of the DES collaboration. Okay, and then last highlight is on the gravitational wave side that we saw from Max on Tuesday, and again showing how you can use these simulation-based inference to get robust posteriors in only seconds compared to the standard MCMC analysis. And I thought it was quite interesting some technical innovations like the group equivariant NPE, where it's just trying to enforce symmetries within the NPE, and also in case you have a likelihood, applying this importance sampling to try to reweight your neuroposterior estimate into the exact thing. Okay, so simulation-based inference also meets interpretability in some of our Astro applications. So this is preliminary work by Kai Lehmann, who also kind of had a similar simulation-based inference setup, this time starting from Galaxy catalogs, where actually he was trying to see whether we could interpret the summaries that are being compressed in this step going from the raw data to the posteriors. And so can we actually try to understand what additional information is being learned by these networks? And so this is just some preliminary work showing correlation between principal components of this learned summaries and known quantities, such as, for example, the power spectrum or actual parameters of the simulation that it was being employed. And you know, even further, Will Handy told us that actually, you know, we are doing all this simulation-based inference with complicated neural networks, but actually when you go close in the parameter space of where the data actually lives, then maybe you don't even need these complicated black box machine learning models, but you can actually do it with linear regression. Okay, so, you know, well, I would say yes, that, you know, all these applications are very successful applications. They're being validated, they're robust, they are applications to data, and they, you know, it's really great work. So if all of this is so successful, you know, why is there still so much skepticism towards machine learning, at least in the Astro community? And, you know, we go to conferences where we have, you know, these debates about machine learning in astronomy and questions like what would it take for the community to accept machine learning findings? So imagine machine learning tells you what the sum of neutrino masses is. You know, what would it take for the community to accept these findings, or is there truth in latent space? And I find it, you know, interesting how the community tends to see machine learning as not just a tool. You know, I've never heard someone say, is there truth in the principal components, or what would it take the community to accept MCMC findings, right? So they seem to place machine learning in sort of a different box that, you know, if it spits out something that we already know, so something that, you know, it reproduces something that we already did traditionally, fine. But if it gives some new insight, then how could we ever trust it? And the skepticism is not just from people that, you know, have never touched machine learning, never trained anything, don't know anything about it, but also comes from people that actually use machine learning in their everyday work, right? So this paper came out claiming that there's like a fundamental difference between machine learning and physics, right? Claiming that machine learning is, you know, fundamentally only about the data and can only be validated on held out training data. And this is, you know, fundamentally in contrast with physics. And so we cannot use machine learning for physics. And I was really surprised to see this, because these definitions that are used, you know, to very strongly define machine learning are also common in many physical models in cosmology. So for example, the NFW model that, you know, some particle physicists will know, it's, you know, one of the most well-accepted models for the internal structure of dark matter halos was also fit to simulated data, just a power law fit to simulated data, and was also validated on held out halos in those same simulations. And so I don't see this machine learning definition as something, you know, that strongly makes a departure from physics, but it's actually just reflects the way machine learning is being used rather than as something intrinsic in machine learning. Okay, so what's the issue, you know, and I feel like the key issue is really about interpretability. And, you know, it's not a warm, fuzzy feeling that I want to, and it's not, forgotten all the ways people have described interpretability now, but it's not this, you know, thing that I want to do only if I don't trust my model, or, you know, I just want to know how the likelihood ratio came about. It's not really that. I see it as the way to do science and try to interpret what the underlying physics that the model is learning. And I actually see it as an opportunity to be able to discover some new insights into things that we cannot model with traditional methods. And there's many of those in cosmology. In fact, most of the nonlinear regime, we typically just throw out in cosmology. We don't even model it because we don't know how to describe it. We don't understand it. And so actually, I see machine learning as a tool that can learn nonlinear patterns, and that if we can interpret, we can actually learn something new about the physics that we would otherwise don't have access to. So I agree that there are certain cases where you probably don't need it. And I think that's when you physically understand your input and your output completely. And so you're just trying to model, you know, a physical process that you fully understand, and you're just trying to model it faster. However, I still think that explainability can help in that regime, and I'll give an example of that at the end of my talk. Okay, so for interpretability, at least on the Astro side, symbolic regression has been suggested as a way to try and find accurate and simple analytic expressions of the data, which could be interpretable because they're just equations. And so this is work by Harry Desmond, and he had this poster showing, for example, this is just one application where they applied their symbolic regression code on. And I completely agree that equations have, for example, higher portability than a neural network. So that if you can completely describe a neural network mapping with an equation, I mean, that's great. That's much better. But I'm not sure our equations are always interpretable, right? You can get a really complicated equation that at the end of the day becomes as complex as a neural network. And also, are they explainable in the sense that can we then relate these equations that are being found to the science domain? So for example, can one interpret whatever analytic expression for the expansion rate of the universe to then some theory that predicts that functional form. And so the way I've been you know, trying to approach this problem has been more from an information theoretic perspective, where essentially the key part is is model compression. So what you want to do is you want to try to compress your information into a low dimensional disentangled latent representation that has all the information that is needed to predict a certain output of interest. So this kind of borrows you know, elements of variational autoencoders, for example, but it's not a variational autoencoder in the sense that it's not unsupervised. You're not trying to reconstruct all the information that you have in your input, but just what's relevant to predict some output of interest. And this is work that I started a couple of years ago mainly with Hiranya Paris and Andrew Ponson. And so one of the first applications that we try to use this model for is for halo density profiles. So in particularly, we were interested in modeling the outskirts of dark matter halos because these have some cosmological interesting features that we wanted to model and where really there is no analytic expression for. And so what we did is that we took some simulations, so centered on a dark matter halo, and we wanted to compress that with a 3D convolution neural network, because it's our data is in 3D, into this low dimensional, disentangled, latent representation, so that it retains all the information to be able to predict rho as a function of R. So that was what we wanted to model, essentially, rho of R, the density profile of these halos. And so what you see here is just an example of the output of that model in blue for a single dark matter halo, and in comparison, the NFW model, which is typically only designed to model halos up to their boundary, up to their viral radius, and not in the outskirts where we were interested in modeling. Okay, so once you have, you've compressed all the information in this disentangled latent representation, how do you actually interpret what that is and what information is encoded in this latent representation? And so what we use for that is mutual information. So mutual information is a very standard metric in information theory that essentially tells you about the relationship between two quantities, not just their linear correlation, but their full statistical dependence. So both linear and nonlinear dependence between these two quantities. And we work quite a bit to come up with a mutual information estimator that's robust, that gives error bars, and this, if you're interested, is the GitHub link is publicly available. And so what we looked at is essentially the mutual information between each latent and the density as a function of radius, so our output of interest. And so how you can see here that you have one latent that has information about the profile up to about half its viral radius, and then no information in the outskirts of this halo. Then you look at the second latent and you say, okay, there's basically no information in this inner part of the halo, but it has lots of information about what's happening in the outskirts of the halo. Then you add a third latent and you say, okay, there's some additional information around sort of the boundary, this R200, the boundary of the dark matter halo. But then when I add a fourth latent, there's basically no information about the latent, about the profile. And so this already tells you about the dimensionality of your problem. So you have 3 degrees of freedom, and those are sufficient to describe the density profiles of halos out to these outskirts of the halo. Okay, and then you can, play around with these latents to see, okay, what is the effect they have on this density profile? So, for example, you can fix 2 of them and vary 1, and you see, okay, this blue latent is actually capturing the normalization of this density profile. Latent B is capturing the slope in the outer part of the halo, and latent C is capturing the inner slope of the profile. Okay, so then you can, we've trained it on this, redshift 0, so the present day structure of the dark matter halo from the simulations, but we can also try to exploit this latent representation beyond its original training task. And in particular, we know from our knowledge of how galaxies form, how structures form in the universe, that really the end structure of these halos is really a result of all the complicated nonlinear gravitational evolution, and so the formation histories of these objects. And so do these latents have information about how these density structures originated? And so what we did is, again, we used mutual information to try to extract this information. And so this is the mutual information between the 2 shape latents, which are really the 2 most interesting parameters, with the mass of these halos, these galaxies, as a function of redshift, and the mass accretion rate, so the rate of change in their mass as a function of redshift. And so you can see, okay, the inner shape latent has a lot of information about what's happening at early times when the halo is forming, when it's forming its bulk in the inner region, and then doesn't really care about what happens at later times. Whereas the outer shape is latent is kind of the opposite, right? It doesn't really care about how it's formed at early times, but is really sensitive to the mass accretion rate of the halo at late times. Okay, so have we learned something new? This is the, another big debate questions that people always ask. Oh, has machine learning, taught us anything new? And I would argue that in this case, yes, right? I mean, machine learning hasn't discovered a new theory of gravity or something, but it has solved a problem that was, a 20-year-old long-standing problem about the connection between the structure of dark matter halos and their evolution history. And in particular, it kind of rediscovered a known relation from about 20 years ago between this inner profile, the inner region, and the early assembly history. But it discovered that for the outer profile, it only depends on one degree of freedom, one component that is related to the most recent accretion history of the halo. And so now we can take these physically interpretable model of the density profile of halos and actually try to fit this to data, because we have data for large halos and then try to, for example, constrain their mass accretion history, given that they have such a tight relation between the fitted parameter and the actual physics that led to that parameter. What about substructures? I mean, there's lots of things, again, that lots of different probes that we have of, for example, the nature of dark matter, and strong lensing observations are one of those. And depending on the properties of these substructures that you find in these strong lensing observations, you can try to exclude different models of dark matter. And so many, results from these kinds of observations have assumed different analytic forms for the density profiles, which in turn very much strongly affect the inferred properties of these subhalos, which then exclude or not exclude different dark matter models. And so basically we wanted to do the same thing, but this time for substructure, looking at more complex simulations that include galaxy formation and baryonic physics to also account for the impact of these uncertain baryonic effects on the profiles of the substructure of these subhalos. And again, we found basically that the very, 3 parameters with clear physical interpretation. Again, we only trained on the present day structure of these subhalos, yet we found parameters that have very clear physical interpretation that can be related to the formation of these subhalos. In particular, one of the parameters is basically sensitive to what these subhalos do before they fall into their parent halo, so they're kind of isolated history. And then another parameter instead becomes very sensitive to the formation history after infalling into the main parent halo. And again, no information was given to the neural network about the formation history of these substructures at all, but it kind of, you're able to sort of rediscover this using metrics like mutual information. And so, yes, we're now, integrating this model within strong gravitational lensing pipelines to reanalyze some of those observations that led to some inferred subhalo properties that look like that wouldn't be predicted by lambda CDM. Okay, so what about, when just your goal is just accuracy, right? So you have an emulator, all you care about is to have an emulator that gives you the most accurate predictions. Can interpretability still be useful? And I think it can be, and this is basically a situation where we were working with this halo mass function emulator, which really, in general, emulators require sampling higher and higher dimensional cosmological parameter spaces if we want to explore beyond the lambda CDM parameter spaces, and are restricted to that kind of domain of validity that you've trained it on. And so can interpreting sort of this mapping from the cosmological parameters to the summary statistic inform, for example, emulators of more efficient training set designs? And so this was work done by Lilian Guo, who just graduated at UCL, where again, we applied a similar network where we wanted to compress the power spectrum into a low dimensional latent representation and then use that to model the halo mass function. And so we wanted to ask questions like, how many parameters are necessary to describe the halo mass function? And can we isolate different information about this quantity? And so again, we found very clear physical interpretation for these, again, 3 disentangled latents, also in this case. And so our idea is basically that instead of you trying to construct emulators that uniformly cover the cosmological parameter space, if you can instead train emulators to cover uniformly the latent spaces, you can actually build more efficient, basically training set for these emulators that might be generalizable to more cosmological models than the one that was strictly trained on in the traditional case. Okay, so let me just end here by saying that I think, you know, machine learning in Astro has already proven successful, in particular at accelerating known physical models that we have. And in the new paradigm of simulation-based inference, I think interpretability is the key in sort of bridging this gap between ML enthusiasts and ML skeptics. And I think explainable AI is a very promising future way to potentially do machine-assisted scientific discoveries. So given that it's the last talk, thank you to Louis and all the organizers for this really nice conference, and I'll stop here.
Thank you for this very clear talk and also for including our great posters of this conference into your highlights. Do we have questions? Last chance to ask questions. Yeah, back there.
Yeah, thank you so much for the talk. I find it really cool to do the explainability part with information theoretical approach. And I think the only one who touched on that, other than Professor Watts as well, had a poster how to explain with information theoretical approach. My naive question is that can you always project your latent space dimensionality into this kind of disentangled low dimensional approach? Can you do that on most of the cases? Is there like a rule to do that, to simplify?
Yeah, so the way you do that is via the loss function. So in the loss function, you essentially have 2 terms. One that is the typical accuracy sort of likelihood term, and then you have a term that tries to promote this disentanglement. And the way we do it is to try to basically push the latent distribution to be as close as possible to independent Gaussians. So this is also what's done in the beta VAE's original papers. And in the applications that we've done, so 4 applications now, we were always able to find a disentangled latent space that would give us the accuracy that was required for our problem. Sometimes it takes a lot of tuning of how you weigh these 2 terms in the loss function, but that's really the only term that takes a lot of fine tuning. But yes, we were always able to achieve this disentangled latent space, yeah.
That's really interesting, yeah. But for us in particle physics, actually, I'm not sure if it would be similar, if this disentanglement can be found somehow, like if we're using simulation-based inference or something else. But that's really interesting. Thank you so much.
Yeah, so it's 2 aspects of interpretability. So regarding explainable AI, machine learning is designed to predict, so it's not designed to explain. And so there could be several or many models that fit the data equivalently as well. And so it seems like if that's the case, you should aim to report them all. Or to retain them in kind of a confidence set of models, of interpretable models, to be probed further. But the second point was that, so scientific understanding presumably relies on interpretability of at least some aspect of the model, but then you could relinquish interpretability of the rest in order to improve inference on that interest part of the model. And in a more traditional statistical context, it's quite well understood how you would do that. So reparameterization, so an interest respecting reparameterization that retains the interpretation of the interest part and could make the rest completely uninterpretable, but allow you to estimate the interest parameter well.
Okay, let me answer your first point. So I think, yes, you're right. Models typically are designed to predict, and this is exactly why we came up with this model. It's designed not just to predict, but to also compress the information into this interpretable latent space. So I guess the point is that we need to rethink some model architecture to not just predict, but also be able to give us or some way of interpreting what the underlying information that is being extracted is. And this is exactly what we try to do here. It's why it's a supervised variational encoder, because it still predicts, but it also gives us the most important degrees of freedom in that prediction. The second point was about, I agree, what you were saying is that you can have some parts that are interpretable and some other parts that, and I think this is also an example of that, right? The convolution neural network, like what it's doing there, I don't really care, or what the actual neurons and the weights and biases of the decoder, I don't care. I care about what information is it learning about my final output, and this by construction is compressed, encoded in this latent representation. So yeah, I agree with that second part as well.
Yeah, and sorry, it wasn't specifically really directed at your talk. It was kind of more.
Yeah.
Thank you.
More questions? Mikhail over here.
So I have a comment on the previous point. So it sounded more to me that the comment was about whether something is identifiable or unidentifiable. And so I'm not sure if interpretable and identifiable are the same. So I'm thinking of like identifiable in a statistical sense. So we have this notion that if you have like certain parameters can be unidentifiable if they can, map to sort of same models in the data space. So I'm not sure like those two things. I mean, those two things are not exactly the same. So it sounds like there might be a bit of a tendency to confuse those two things. I mean, I think an unidentifiable thing can be interpretable. It's just the interpretation is that you don't have information about something. So like, I mean, like having no information about something, this is already, that can be interpreted as something. You have learned something. So not knowing anything is something. Okay, this is getting a bit philosophical. But anyways, I think there was these are two different things, right?
What are the two different things?
So in statistics, we have this notion of an unidentifiable parameter. So if you have a model that can map two different parameters to the same data distribution, we call that an unidentifiable parameter. And I think the comment, I'm not sure who made the comment because I can't see up there, but oh yeah, okay, so that's why.
Yeah, but those are.
I mean, did you mean unidentifiable or something else?
Actually, we could take your linear regression example with quite a good one. So in that context, so this is really illustrating what I meant. So you can get the same prediction from you can take that you can set lots of those beta parameters in the linear regression to 0, and there can be lots of different combinations of variables that will give you the same prediction. So they fit identically well. And in that case, you would have lots of models that are essentially equivalent. They're equally compatible with the data. And what you want to do is to say, these are all the ones that are equally compatible with the data. We want to retain those as plausible explanations and try and refine those conclusions later by probing the thing?
I don't think so, no. So I think those parameters are in the neural network, are the weights and biases of the neural network. So those can take many different values and you might still get to the same result. But the disentangled linear space is not like that. It's constructed to be as close as possible to a prior that I've said. And it has to have all the information in order to give me the predictions about the profile. So in some sense, it has to be the degrees of freedom of your output. Whereas the network parameters, I agree, you could have many different values of that lead to the same model. But by construction, that's not true for the latent space in this construction.
Yeah, sorry, I don't think I'm speaking specifically about your problem. I think it's more general than that. But
Yeah, I think we are both thinking of more generally, like not within the specific model, but just more
Yeah.
like this picture there. So this is what I would call
Exactly, yeah.
unidentifiable, right? And
Right.
that is information. Like if your interpretation of like not this model, but just more generally, like a generic machine learning model, if the interpretation is that there's multiple different sort of explanations of my data, that is an interpretation. That is actually information. So anyway, maybe this is getting a bit kind of too abstract. So okay, yeah, I'll stop there.
Okay, I mean, I think that there are multiple parameters, multiple models that can get to the same data is true, but I don't see the deep philosophical part of it.
Yeah, we can maybe offline.
Okay.
Other questions? If not, then I suggest we thank Louise again. And then to close off, Louis wants to say a few words, but before he does, I would like us all to please give a big round of applause for Louis himself.
So, okay, thanks everybody for that. Really, I just want to say a few words of thank you. First of all, to Imperial for hosting this meeting. It was very much the sort of the different topics or fields of research that people come from, very much aligned with the interests of Imperial's research program. So it was very good to have you here, and thanks to Imperial. A really big thanks to the local organizing committee, who did an awful lot of work before the meeting and also during the meeting. So Rob, sitting over there, is the chair of the local organizing committee, and so it worked very well under him. So thanks to Rob, who was also the official photographer of the meeting. The other part, which I thought went really, really well, was the audio-visual part, in that, I mean, we barely noticed that there could be problems with it. And I think that is real thanks goes to Marvin over here, who I think actually also gets the, if there was an award for the person who spent most time in this meeting listening to what was going on, Marvin would easily be the winner. So thanks, Marvin. That really went well. Obviously, we want to thank the speakers over the last 3.5 days. That made the backbone of the meeting. I don't want to sort of select any particular person, but I think that a big thanks also goes to the highlight speakers who had to sort of concentrate for 3 days or 3.5 days, and did a great job in sort of summarizing the meeting for us. It's good that we've got the recordings of the meetings. They'll appear on the website. There are certainly talks that I want to hear again to sort of try and understand them better. So look out for them on the website coming up. Thanks to the chairpersons. We've done a great job by and large in finishing on time, which quite surprised me. And so that we had sort of more or less enough time for the breaks. the tea break, the coffee breaks and lunch and the dinner last night. They provided an excellent time for people continuing the discussions that sort of started here. Particularly the one last night seemed to go, the discussions went on well past closing time. So it showed the degree of interaction of people here. And actually, we are particularly interested to know if people, as a result of this meeting, have set up sort of collaborations, working together that weren't in existence beforehand. I mean, PHYSTAT does aim to put together, well, originally it was statisticians and particle physicists, but now it's statisticians, machine learning, particle physicists, and astrocosmo people. So just send me an email if you're doing anything along those lines. Thank you also to the poster presenters, which I think were equally as important. There were very lively discussions going on there. And really congratulations to Declan Bartlett and to Tom Runting for winning the prizes for the posters. I hope the remote participants as well managed to get a little bit of the dynamic feeling for what was going on here in the meetings and in the discussions. Thanks also to the sponsors for our meeting. They have magically appeared up here. So these all provided financial help. So we're really grateful to all of them. You can see them if you want to see who it was afterwards. You can find them on the website. The other thing that we will sort of keep you informed about is just the idea of having some sort of record of this meeting, not proceedings, but maybe a book, a real book, or an electronic version of it, of perhaps not exactly the meeting, but we will sort of think about choosing topics that were inspired by this meeting, and have people who spoke here and also people who didn't speak here contributing to us. So that's not cast in stone by any means yet, but we'll keep you informed about how that idea progresses. The person who really is in charge of it is Lydia over here. So I hope all of you will be joining future PHYSTAT events. We have them sporadically, so you have to keep a look on the website to see when they're coming up. And they will be under new management with Lydia and Olaf Benke, who was here till yesterday, sort of running PHYSTAT from now on. So hope to see you around at future meetings. Thank you, everybody. Okay, safe journey home.
Just in case you wanted 5 minutes left.
Hi. Yeah, well. Yeah. Well, that's nice. Yeah. Okay.
Well done, crikey. I mean, I think you did the
Recording stopped.